A momentous scientific revelation has just been unveiled, fundamentally altering our understanding of the interstellar visitor known as 3 Atlas. Merely 2 weeks ago, on October 24th, an unprecedented event occurred in the annals of radio astronomy. As 3 Atlas traversed our solar system, it emitted a distinct radio signature. This detection has been unequivocally verified, and the chemical composition identified is indeed genuine: hydroxyl radicals, the product of water molecules disintegrating under stellar radiation. However, what truly perplexes and keeps researchers engrossed is the origin of this signal. It emanated from the identical celestial sector as the renowned WOW signal detected in 1977. This is in addition to the 8 other documented anomalies, the inexplicable alterations in its trajectory, and a fleeting observation window so narrow that its discovery was almost a matter of chance. Join me as we delve into this late-night investigation, and by its conclusion, you will grasp why this discovery is truly transformative. If these unfolding events have captured your imagination as profoundly as they have mine, please consider expressing your engagement by hitting the like button and subscribing to ensure you remain abreast of every development as this narrative unfolds in real time. Share your location, the current time where you are, and your thoughts on this remarkable new finding in the comments section. Your support is instrumental in our pursuit of stories like this, and for that, we are incredibly grateful. Part 1. A faint signal from the depths of space. October the 24th, 2025, 4:10 in the morning, Universal Time. A significant portion of South Africa was still enveloped in the tranquil darkness of night, beneath a sky adorned with countless stars. It was the kind of profound darkness that evokes a sense of standing at the precipice of existence. Yet, within the Karoo Desert, 64 colossal radio dishes were fully operational, their surfaces meticulously angled towards a particular region of the sky, so proximate to the sun that observing it presented an almost insurmountable challenge. The Meerkat Radio Telescope Array, one of humanity's most exquisitely sensitive radio instruments ever constructed, was engaged in its primary function, attuning to the subtle transmissions emanating from the cosmos. And on that specific morning, it registered something entirely unexpected. 2 absorption lines materialized within the data stream. Though faint, barely discernible from the ubiquitous background hiss of the universe, they possessed a discernible structure, appearing deliberate. The frequencies were remarkably precise: 1,665 MHz and 1,667 MHz. For anyone familiar with radio astronomy, these figures are guaranteed to quicken the pulse. They correspond to the primary spectral lines of hydroxyl radicals, the OH molecule, a chemical indicator that manifests when water is dissociated by the intense radiance of ultraviolet light. This was not mere static, nor interference from a passing satellite, nor a malfunction of the equipment. This was chemistry broadcasting itself across hundreds of millions of kilometers of vacant space, originating from an object that was unequivocally not part of our solar system. The celestial body in question had been catalogued as 3 Atlas, bearing the designation C/2025 and 1. The I signified its interstellar origin, marking it as the 3rd confirmed visitor from beyond the gravitational dominion of our Sun. It had been initially discovered earlier that year, hurtling inwards on a hyperbolic trajectory that unmistakably signaled its extraterrestrial nature. Astronomers had been diligently tracking its progress for months, observing its increasing luminosity as it approached perihelion, its closest orbital point to the Sun. They had meticulously measured its velocity, calculated its orbital path, analyzed its tail formation, and documented its fluctuations in brightness. However, no human on Earth had ever before detected a radio signal emanating from an interstellar object. Never. In the entire history of radio astronomy, dating back to 1930, when Karl Jansky first detected radio waves originating from the Milky Way, Such an occurrence had been unheard of. Let us be unequivocally clear about the implications of hydroxyl radicals. When water molecules are subjected to ultraviolet radiation from a star, they do not merely evaporate serenely. They fracture, they break apart into their constituent elements. Hydrogen atoms are propelled in one direction, while hydroxyl radicals, those OH molecules, linger behind like spectral remnants. They possess the property of absorbing very specific wavelengths of radio waves, thereby creating discernible dips in the spectrum precisely at 1665 and 1667 MHz. This phenomenon represents one of the most fundamental signatures of water chemistry observed throughout the universe, and it is the very same chemistry that underpins the existence of life on Earth. Every droplet of water within your being, every molecule composing the 70% of your body that is water, can, under the appropriate conditions, decompose into these very same radicals. Consequently, when astronomers observe hydroxyl absorption lines in the vastness of space, they are, in essence, witnessing the chemical fingerprints of H2O, the universal solvent, the very liquid that made biological processes possible. But herein lies the perplexing aspect. This detection was not a random occurrence from some distant comet in the outer solar system or a nascent nebula in a faraway galaxy. It originated from 3 Atlas, an entity that had sped potentially millions, if not billions, of years traversing the unlit void between stars, carrying within it an unknown quantity of ice and organic compounds on its surface. And now, as it made its passage past our Sun, it was releasing these volatile substances, allowing radio telescopes to ascertain its composition in real time. For the first time in human history, we were obtaining direct chemical insights from interstellar material, not through the deployment of probes to collect dust particles, but by interpreting the radio whispers of molecules disintegrating amidst the cosmic expanse. The scientists who first analyzed the data responded with their customary scientific skepticism. They cross-referenced the signal against extensive databases of radio frequency interference. They scrutinized the vicinity for any orbiting satellites. They meticulously compared the time of detection with known sources of terrestrial noise. They even reviewed records from 2 prior observation attempts conducted on September 20th and September 28th, both of which yielded no discernible signal, only silence. Thus, the question arises, why did it manifest on October 24th? What had changed? The answer, as it transpired, was intricately linked to geometry and precise timing, 2 factors that rendered this detection not merely unusual, but extraordinarily improbable on a cosmic scale. Subsequently, an even more startling observation was made, sending a wave of disquiet through the astronomical community. The celestial coordinates where 3 Atlas was situated at the moment of detection, the precise celestial location from which those hydroxyl absorption lines emerged, corresponded with uncanny proximity to another renowned celestial landmark. This region of space had, 48 years prior, been the source of the most celebrated unexplained radio signal in the history of the search for extraterrestrial intelligence. You are likely familiar with its moniker, the WOW signal. On August 15, 1977, the Big Ear radio telescope in Ohio captured a narrowband signal of such remarkable strength and precise structure that the astronomer Jerry Emmon famously circled it on the printout and inscribed the word "Wow" in the margin. The signal persisted for 72 seconds and never reappeared. It originated from the constellation Sagittarius, and despite decades of subsequent observations, its source has never been definitively identified. Was it of extraterrestrial origin? Was it a comet? Or was it some extraordinarily peculiar astrophysical phenomenon that currently eludes our comprehension? The question remains open. Yet, now, almost half a century later, another interstellar enigma was unfolding in virtually the same sector of the sky, separated by a mere 9 degrees of arc. This proximity is sufficient to prompt contemplation on whether a certain region of space possesses an innate gravitational pull for unusual signals, akin to a flame attracting moths. Let me be perfectly clear. This is not being presented as a message. No one is asserting that 3 Atlas is broadcasting a greeting or transmitting a comprehensive cosmic encyclopedia. The detected phenomenon is an absorption line, not an active transmission. It is indicative of chemistry, not communication. However, the intricate structure, the remarkable precision, the sheer improbability of its detection, coupled with the unsettling resonance with the WOW signal, has collectively ignited a fervent atmosphere of speculation. Online forums erupted with discussions. SETI researchers commenced drafting new observation proposals. The popular press featured headlines heralding interstellar whispers and alien chemistry. Meanwhile, behind the scenes, the scientists continued their diligent work, measuring, calculating, systematically eliminating the impossible, and striving to elucidate the improbable. Thus, a pivotal question looms over this entire narrative, a question that will profoundly influence every aspect of our subsequent discourse over the following 15,000 words. When the universe communicates, how do we discern whether its voice is natural or intelligent? How do we differentiate between the random static of chemistry and physics, and a deliberate signal from an entity that intends to be heard? And perhaps, just perhaps, the question itself is fundamentally flawed. It is conceivable that nature and intelligence are not mutually exclusive. It is possible that the boundary between them is far more ambiguous than we have ever conceived. Because on this occasion, the whisper did not originate from a star, a pulsar, or a black hole. It emanated from an object in transit, something that does not belong within our cosmic neighborhood. Something that carried across the unfathomable gulfs between stars a message inscribed in the most ancient language known to the universe: water disintegrating under stellar light. Part 2. The observational geometry and timing that enabled it. It is imperative to grasp the extraordinary improbability of this detection. At the precise moment when Meerkat registered those hydroxyl lines, 3 Atlas was situated a mere 3.76 degrees from the Sun. To provide context, imagine holding your fist at arm's length and extending your thumb. This encompasses approximately 2 degrees of the sky. Now, envision attempting to observe an object located less than twice that distance away from the brightest celestial body in our daytime sky. The Sun inundates the entire electromagnetic spectrum with an overwhelming torrent of radiation, effectively obscuring everything in its vicinity with a blaze of radio noise. Most radio telescopes refrain from attempting observations so close to the solar disk due to the pervasive interference that completely overwhelms any faint signals. It would be akin to straining to hear a whisper amidst the deafening roar of a rock concert while standing directly beside the loudspeakers. However, as it turns out, geometry plays a pivotal role in astronomical observations. The proximity of 3 Atlas to the Sun, while posing observational difficulties, actually proved advantageous. Here's the reason. As an object traverses space, its velocity induces a Doppler shift in any radiation it emits or absorbs. If it is moving towards us, wavelengths contract and shift towards the blue end of the spectrum. Conversely, if it is moving away, they elongate and shift towards the red. 3 Atlas was traversing the inner solar system at an angle, not directly towards or away from Earth. This specific trajectory meant that its hydroxyl absorption lines were Doppler shifted away from the Sun's overpowering radio output. The recorded velocity was negative 5.66 kilometers per second. This recession velocity was sufficient to displace those 1,665 MHz lines just far enough from the solar background that Meerkat's receivers could discern them amidst the noise. The width of these lines was equally informative, measuring between 0.9 and 1.3 kilometers per second. They were narrow, precise, and consistently reproduced across multiple scans within the observation window. Had this been attributable to instrumental noise or radio interference, the lines would have exhibited greater breadth, appeared more chaotic, and lacked consistency. However, they remained remarkably stable, akin to a tuning fork resonating at a singular, clear frequency. The data integrity checks successfully passed every scrutiny. The signal was unequivocally real and originated precisely from the location predicted by 3 Atlas's ephemeris, the calculated celestial path used by astronomers to determine where to direct their instruments. Now, let us address the reasons for the failure of earlier attempts. On September 20th and September 28th, observatories across the globe attempted to detect 3 Atlas within the radio spectrum. The outcome was complete silence. No hydroxyl signals, no emission lines, no absorption features. The reason? It can be attributed to the phase angle and solar heating. In late September, the comet remained too distant from the Sun, its temperature too low to facilitate significant sublimation of its water ice. The surface temperature hovered below the critical threshold at which volatile substances begin to readily vaporize. However, by late October, the situation had dramatically changed. The object was merely days away from its perihelion, scheduled for October 29th, and the Sun's radiation was intensely impacting its surface. Ice that had remained frozen for millennia was finally beginning to warm, fracture, and release gases into the tenuous coma surrounding its nucleus. Accompanying this gaseous release were hydroxyl radicals, billions upon billions of them, forming a cloud that absorbed radio light at the exact frequencies Meerkat was engineered to detect. The temporal window for this observation was exceptionally narrow. If it had been too early, the volatile compounds would not have been released. If it had been too late, the object would have passed behind the Sun from Earth's perspective, rendering it entirely unobservable. October 24th fortuitously fell within this optimal period, a brief interval where the geometry aligned perfectly, the chemical reactions were activated, and the instrument's sensitivity matched the signal's strength. Had Meerkat conducted observations even 48 hours later, the detection might have proven impossible, as the solar conjunction would have completely obscured the object, shielding it behind an impenetrable wall of radio interference that no terrestrial telescope could penetrate. Let us momentarily broaden our perspective to consider the implications of this event for the broader study of interstellar objects. 3 Atlas represents only the 3rd confirmed visitor from beyond our solar system. The first, Oumuamua, passed through in 2017, leaving astronomers perplexed by its unusual acceleration and the absence of a visible coma. The second, Borisov, appeared in 2019 and behaved like a conventional comet, complete with a dust tail and predictable outgassing. And now we have 3 Atlas, which appears to occupy a middle ground, exhibiting predominantly cometary characteristics, but with sufficient peculiarities to keep researchers thoroughly engaged. The very fact that we are detecting radio signals from such an object constitutes a paradigm shift in our methodology for studying these celestial bodies. Prior to this, our reliance was primarily on optical telescopes for tracking, spectrographs for analyzing reflected sunlight, and perhaps occasional infrared measurements for gauging temperature. Radio detections were simply not considered a viable possibility. Meerkat's exceptional sensitivity in the L-band, the radio frequency range approximating 1.4 GHz, renders it uniquely equipped for this type of investigation. The array comprises 64 dishes spread across 8 kilometers of South African desert. Each dish, measuring 13.5 meters in diameter, operates in unison, creating an effective aperture far exceeding that of any individual telescope. The correlator seamlessly merges signals from all 64 dishes in real time, effectively filtering out interference, amplifying coherent sources, and producing spectral data with sufficient resolution to isolate individual molecular lines. It is a testament to technological innovation, situated in one of the most radio-quiet locations on Earth, legally protected from the pervasive radio frequency pollution that plagues observatories in more populated regions. However, the narrative takes an even more intriguing turn. The orbital path of 3 Atlas is not random. It is remarkably aligned with the ecliptic plane, the flat disk upon which most planets orbit the Sun. Interstellar objects, by their very definition, originate from outside our solar system, implying they could approach from any direction, as the galaxy is a three-dimensional entity. Objects originating from the galactic halo should logically approach at steep angles, descending from above or ascending from below the solar system's plane. Yet, 3 Atlas arrived on a nearly horizontal trajectory, as if adhering to the same planar geometry that governs planetary orbits. This is an unusual characteristic, not impossible, but sufficiently anomalous to raise scientific curiosity. Some researchers have posited that this might suggest a local origin, perhaps from a neighboring star system whose orbital plane coincidentally aligns with ours. Others propose it is merely a statistical anomaly, the kind of coincidence that arises as the sample size of detected objects increases. Furthermore, there is an unspoken question that many are contemplating. Could the geometry itself, the near-solar alignment, the specific phase of volatile release, be amplifying something that would otherwise remain undetectable? Is there a mechanism, as yet unknown to us, that facilitates an interaction between the solar wind and the outgassing ice, inadvertently generating a structured radio signature? The fundamental laws of physics permit a wide array of unexpected emergent behaviors. Chaos theory demonstrates how simple systems can give rise to complex patterns. Self-organization is a pervasive phenomenon observed throughout nature, from the intricate structure of snowflakes to the vast architecture of galaxies. It is plausible that what we are observing is not a deliberate message, but neither is it entirely random. Perhaps it represents something in between, a natural phenomenon that appears intentionally designed due to the inherent order present within its underlying chemistry and physics. The perihelion approach, scheduled for October 29th, was just 5 days after the detection. As the comet reached its closest point to the Sun, solar heating would have reached its zenith, volatile release would have maximized, and the entire object would have been enveloped in a dense shroud of gas and dust. If hydroxyl production scales directly with temperature, then the signal should have intensified significantly in the final days preceding perihelion. However, did it? This is one of the critical questions that follow-up observations are endeavoring to answer, assuming, of course, that the orbital geometry permitted any observations during that crucial period. The Sun acts as both an enabler, by heating the ice to release the molecules, and a barrier, by overwhelming the signal with its own radio emissions. Sarla, the South African Radio Astronomy Observatory, logged the detection within a matter of hours. The data underwent their standard verification protocols, including automated flagging of radio frequency interference, visual inspection by trained astronomers, cross-referencing with known celestial sources, and consistency checks across various frequency channels. Every parameter passed. The hydroxyl lines appeared precisely where theoretical models predicted, exhibiting the correct Doppler shift, the correct line width, and the correct relative intensities. This was not a random occurrence. It was not an error. It was genuine, reproducible, and profoundly perplexing. Not because it defied the laws of physics, but because it confirmed that interstellar objects, these cosmic wanderers born in the icy fringes of alien star systems, harbor the same fundamental chemistry that underpins life on our own planet. And now, for the first time, we possess the means to listen to it. Part 3. What exactly was detected? Chemistry, not a beacon. Let us establish one crucial point from the outset. This is not an extraterrestrial transmission. I am aware that recent headlines may have fostered the impression that we have intercepted a missive from another civilization, But that is not the case. What Meerkat detected was an absorption line, not an emission. The distinction is critically important. An emission line signifies radiation being actively generated and broadcast by a source, akin to a radio station transmitting a signal. Conversely, an absorption line represents the opposite, a discernible void or dip within the spectrum, a shadow created by the removal of light at a specific frequency. Consider it analogous to observing sunlight through a prism. You perceive a spectrum of colors, but upon closer examination, you will notice thin, dark lines traversing it. These lines occur where elements within the sun's atmosphere have absorbed particular wavelengths of light. These are absorption lines, and they provide information about the sun's composition without the need for physical contact. The hydroxyl radical, OH, is one of the most significant molecules in astrochemistry. It forms when water molecules are dissociated by ultraviolet radiation, a process known as photodissociation. When a water molecule, H2O, is struck by high-energy ultraviolet photons from a nearby star, it fractures into hydrogen and hydroxyl. The hydrogen, being lighter and faster, dissipates into space. The hydroxyl, however, persists for a longer duration, absorbing radio waves at its characteristic frequencies, 1665.402 MHz and 1667.358 MHz. These are referred to as the main lines of interstellar OH and have been utilized for decades in the study of star-forming regions, supernova remnants, and, notably, comets. Indeed, comets are prolific producers of hydroxyl radicals. Every comet within our solar system generates hydroxyl as it approaches sufficiently close to the Sun. This phenomenon serves as one of the primary observable indicators used by astronomers to quantify water production rates. Direct observation of water vapor in the optical spectrum is not feasible because it does not efficiently emit or absorb visible light. However, hydroxyl, on the other hand, becomes highly detectable in the radio and ultraviolet bands, shining like a beacon. To ascertain the volume of water a comet expels into the void, scientists measure hydroxyl compounds and extrapolate backward. This is a well-established methodology, rigorously tested over decades of cometary research. What distinguishes the detection of Oumuamua, initially designated 3I/2017 U1 and later referred to by various informal names such as Oumuamua itself, and now often discussed in the context of interstellar object investigations, is not the fundamental chemical analysis, but rather the location of this activity. At the moment of observation, Oumuamua's surface temperature was estimated to be approximately 230 Kelvin. While this is frigid by earthly measures, equivalent to around -43 degrees Fahrenheit, it is sufficiently warm for water ice to transition directly from a solid state to a gaseous one through sublimation, bypassing the liquid phase. At this temperature, the ice begins to fracture, releasing vapor into the surrounding vacuum, which forms what astronomers term a coma, a tenuous atmosphere of gas and particulate matter that encircles the comet's core. This coma expands as the comet draws nearer to the Sun, escalating from a few hundred kilometers in diameter to tens of thousands of kilometers, contingent on the comet's reservoir of volatile substances. Within this coma, chemical transformations occur. Water molecules dissociate, generating hydroxyl radicals, and with considerable fortune and a radio telescope precisely tuned to the correct frequency, these can be detected. The signal captured by the Meerkat telescope exhibited no modulation. There was no intermittent pulse, no recurring sequence, and no amplitude variation to suggest intentional encoding. It presented as a steady absorption feature, a dip in the background radio spectrum, appearing precisely where hydroxyl radicals were anticipated, given the comet's velocity and spatial coordinates. Were this a genuine technosignature, indicative of deliberate creation by an intelligent civilization, one would anticipate inherent structure within the signal. This would involve information encoded through frequency modulation, amplitude modulation, or phase shifts, hallmarks of design intent. The renowned 1977 WOW signal, despite its enduring enigma, was characterized by its narrow bandwidth and high intensity, attributes that marked it as potentially artificial, even in the absence of repetition. The signal from Oumuamua, however, aligns perfectly with natural chemical processes. In essence, it is an unexceptional finding from a chemical standpoint, rendered extraordinary by its origin from an object traversing interstellar space. For comparative context, let us examine the characteristics of a genuine artificial signal. Within the realm of SETI research, the benchmark for a potential alien transmission is a narrowband signal, one that is spectrally purer than any phenomenon produced by nature. Pulsars, for instance, emit radio waves, but these are dispersed across a broad spectrum of frequencies. Hydrogen clouds in space radiate at a wavelength of 21 centimeters, but this emission line is also broad, its shape influenced by thermal motion and turbulent dynamics. A deliberate transmission would be exceptionally sharp, occupying a minuscule portion of the spectrum, as this represents the most efficient method for conveying information within a limited bandwidth. Furthermore, one would expect some form of encoding, such as prime numbers, mathematical constants, or image data, any element that distinguishes it from random cosmic noise. The hydroxyl spectral lines emanating from Oumuamua lack any such features. Their width precisely matches what would be expected from thermal and turbulent motion within the coma. Their intensity is precisely as predicted based on the solar radiation incident upon the nucleus. Their Doppler shift is precisely in accordance with velocity measurements. However, there is a profound aspect to this discovery, even if it is not a technosignature. It represents a biochemical fingerprint from an object originating beyond our solar system. Consider this for a moment. For the first time in human history, we have directly analyzed the chemical composition of material that originated in a star system other than our own. We have confirmed that ice formed around a distant sun, having traversed light years of empty space, still contains water and behaves identically to the ice found within our solar system. The fundamental laws of chemistry are universal. The very molecules that are essential for life on Earth are present elsewhere, drifting through the galaxy aboard comets and asteroids, and potentially countless other cosmic bodies. This observation substantiates a core tenet of astrobiology, that the fundamental constituents of life are not unique to our planet but are ubiquitous. The parallels with observations of comets within our solar system are striking. During the European Space Agency's Rosetta mission, which closely studied comet 67P/Churyumov-Gerasimenko, water vapor, hydroxyl radicals, carbon dioxide, methane, and ammonia were detected, all the volatile compounds expected from a dusty ice ball warmed by the sun. The Swift UV telescope, which observed Oumuamua in the weeks preceding its closest approach to the sun, confirmed signatures of water sublimation in the ultraviolet spectrum. Independent analyses from ground-based optical telescopes tracked variations in brightness and dust production. All indicators aligned consistently. This object was exhibiting behavior consistent with that of a comet, producing characteristic chemical signatures and releasing gas at a rate predictable for its size and proximity to the sun. The sole discrepancy is its origin. It did not form within our solar system but elsewhere, orbiting a star that will likely remain unidentified. It is now transiting our cosmic neighborhood on a singular trajectory that will propel it back into interstellar space at a velocity exceeding 40 kilometers per second. The surface temperature of 230 Kelvin is optimal for sublimation. If it were colder, the ice would remain bound by molecular forces requiring more energy to overcome. If it were warmer, explosive outgassing, sudden ejections, and potentially catastrophic fragmentation could occur. 230 Kelvin represents an ideal balance, a temperature at which water ice undergoes a gentle transition from solid to gas, releasing volatiles in a steady, manageable stream. This is the same temperature range where comets within our solar system become notably active, developing tails, increasing in brightness, and becoming the celestial spectacles that ancient civilizations once interpreted as portents. Oumuamua, due to its size and trajectory, is unlikely to become a naked-eye comet. It is too small and faint, approaching the Sun at an angle that largely conceals it within the Sun's glare. However, for radio astronomers, it represents a remarkable phenomenon, a real-time chemical analysis of interstellar ice, broadcasting its composition across the electromagnetic spectrum. The absence of modulation implies no deliberate message. Yet, it signifies something else as well. This is unadulterated, unprocessed chemistry. To conceal a signal within natural phenomena, one would need to introduce modulation, alteration, and encode information in a manner that stands out against the background. The fact that the hydroxyl spectral lines from Oumuamua are indistinguishable from natural cometary emissions suggests either a purely natural origin, the most parsimonious explanation, or that any hypothetical intelligence possessing the capacity to manipulate chemistry at this level is so advanced that it can perfectly replicate natural processes. If such an advanced civilization can engineer synthetic comets that mimic real ones precisely, then we are encountering intelligence operating on a scale far beyond our current comprehension, rendering detection practically irrelevant. Therefore, the conclusion is this: the signal is chemical in nature, hydroxyl absorption, a textbook example, precisely what one would expect from a comet containing water ice approaching the Sun. However, this chemistry is occurring on an object from interstellar space, elevating it from a routine observation to a historic one. It demonstrates that comets originating outside our solar system can transport the precursors of life across the galaxy. It illustrates that water, the most crucial molecule for biology, is abundantly present throughout space, locked within grains, pebbles, and boulders that traverse the interstellar medium. And it reveals that with the appropriate instrumentation, precise timing, and a degree of good fortune, we can, in real time, eavesdrop on the chemical symphony of the cosmos. Even if Oumuamua is not transmitting a message, it is broadcasting something equally significant: empirical evidence that the chemistry foundational to life is universal, ancient, and intrinsically woven into the very fabric of the galaxy. Part 4 delves into anomalies, peculiarities, and the lingering echo of the WOW signal. Yet, had Oumuamua behaved as a typical comet, adhering to predictable physical laws, this discussion would not be taking place. The detection of hydroxyl is only one facet of the narrative. As the object neared its closest approach to the Sun, researchers documented not one, not two, but 8 distinct anomalies in its behavior. These represented deviations from what would be expected from a simple icy body traversing the inner solar system. These included unusual tail dynamics, erratic fluctuations in brightness that defied conventional models of dust production, off-axis jets emanating from directions seemingly inconsistent with direct solar heating, and perhaps most perplexingly, the formation of both a tail and an anti-tail, 2 opposing streams of dust suggesting a more complex process than ordinary outgassing. Let us begin with the tails, as they are the most visually arresting. As a comet approaches the Sun, solar radiation pressure and the solar wind expel dust and gas away from the nucleus, forming a tail that invariably points away from the Sun. This is one of the most consistent characteristics of cometary behavior. Yet Oumuamua developed what observers described as an anti-tail, a secondary stream of dust directed towards the Sun. While anti-tails are not entirely unknown, they can manifest as perspective artifacts when Earth passes through a comet's orbital plane, creating the visual impression of a sunward-pointing tail when in reality one is observing dust particles released earlier that are now trailing the nucleus. However, the symmetry in this particular instance was peculiar. The main tail and the anti-tail exhibited comparable brightness and length, as if the comet were expelling material in two diametrically opposed directions simultaneously. This would necessitate asymmetric outgassing jets originating from specific points on the rotating nucleus, which in turn implies an irregular surface with concentrated deposits of volatile materials. NASA's space weather reports highlighted these tail dynamics as noteworthy. The main tail displayed oscillations, a wobbling motion over several hours, suggesting that the direction of gas release varied with the nucleus's rotation. If the nucleus were spinning rapidly and active regions on its surface faced different directions as it rotated, one would anticipate the tail to exhibit a shimmering or shifting pattern. However, the magnitude of these oscillations appeared excessive. Rotational models suggested a nucleus spin rate of once every 8 to 12 hours, typical for smaller cometary bodies. Yet, the tail behavior implied either a faster rotation or a highly elongated shape that generated significant torque during rotation. In either scenario, it did not conform to the profile of a simple, spherical snowball melting under the sun. Fluctuations in brightness further compounded the mystery. Optical telescopes monitoring Oumuamua reported magnitude variations of nearly 2 full magnitudes over a period of 1 week, a significantly greater fluctuation than would be attributable to rotational modulation alone. A 2-magnitude change corresponds to an approximately 6-fold increase in brightness, necessitating either a sudden surge in dust production or a shift in viewing geometry that exposed a more reflective surface. However, the orbit was well defined, the viewing geometry predictable, and no sudden outbursts were observed in real time. The brightness simply changed gradually but substantially, as if the comet were dimming and brightening in response to factors not immediately evident from the data. Off-axis jets provide an additional indicator of unusual activity. Jets are common phenomena on active comets, representing localized areas of intense sublimation, frequently concentrated at the subsolar point, the region of the surface directly facing the sun. However, Oumuamua exhibited jets emanating from areas not directly illuminated, suggesting that subsurface heating was driving the outgassing. Sunlight could penetrate the outer layers of ice, be absorbed below the surface, heat the interior, and build pressure until gas erupted through fissures and vents. This process can create jets directed in virtually any orientation, contingent on the location of these vents. However, it also points to a complex internal structure, with layers of ice possessing differing compositions and thermal properties, rather than a homogeneous mass of frozen water. Adding to the intrigue is a persistent coincidence: the celestial location. At the time of the hydroxyl detection, Oumuamua was positioned at approximately 19 hours right ascension and a declination of -27 degrees. The WOW signal, detected 48 years prior, originated from a region near 19 hours 25 minutes right ascension and 26 degrees 45 minutes declination. This represents a separation of roughly 9 degrees, a proximity that places them within the same general celestial sector, specifically near the constellation Sagittarius, close to the galactic center. 9 degrees is not an insignificant angular distance. It is 18 times the apparent diameter of the full moon. However, on the celestial sphere, which spans 360 degrees in all directions, this proximity is remarkably close. This closeness prompted SETI researchers, upon the news of the detection, to retrieve archival data, compare findings, and investigate any potential correlation. The WOW signal remains one of astronomy's most celebrated unresolved mysteries. On August 15, 1977, the Big Ear Radio Telescope in Ohio recorded a 72-second burst of narrowband radio energy at 1,420.456 MHz, adjacent to the hydrogen line at 1,420.406 MHz. The signal was so powerful that it registered as a 6 on a scale, where one represents typical background noise. Jerry Inman, the astronomer reviewing the printout, was so astonished that he circled the alphanumeric sequence on the computer paper and annotated it with "wow" next to it. Subsequent observations yielded no results. Hundreds of hours of listening time over subsequent decades produced no repetitions, no similar signals, and no definitive explanation. Theories range from extraterrestrial transmissions to interstellar clouds amplifying natural emissions, to comets releasing hydrogen, though none of these explanations fully reconciled the available data. Now, nearly 50 years later, we are confronted with another anomalous signal originating from a remarkably similar region of space. Could this be mere coincidence? Absolutely. The sky is vast, but certain areas attract more scrutiny than others. Sagittarius, being located towards the galactic center, is a favored target for astronomical surveys, leading to a greater volume of data and a higher probability of detecting unusual phenomena. Nevertheless, the temporal alignment and the chemical nature of the signals have garnered significant attention. The confluence of both signals involving radio frequencies, both representing unexpected detections, and both originating from sources that defy simple explanations, creates a pattern that is difficult to disregard, even if it is likely coincidental. Avi Loeb, the Harvard astronomer known for his provocative perspectives on interstellar objects, characterized the hydroxyl detection as the inaugural radio signal emanating from Oumuamua, carefully framing it as a milestone in interstellar chemistry rather than a technosignature. However, the phrasing itself carries weight. First radio signal from an interstellar object sounds commonplace until one recalls that we have confirmed the existence of only 3 such objects, and 2 of them remained radio silent throughout their passage through our solar system. So why did this particular object speak? What sets Oumuamua apart? Is it richer in volatile compounds? Is it larger? Did we simply benefit from fortunate timing and geometry? Or is there something inherent in its composition, its structure, or its origin that renders it distinctive? Skeptics predictably contend that this is merely typical cometary behavior amplified by solar heating. And they are likely correct. The most straightforward explanation, one that necessitates no new physics or speculative leaps, is that Oumuamua is an ordinary comet, albeit one that formed in a different star system. The anomalies observed in its tail, brightness, and jet activity are unusual but not unprecedented. Comets are inherently complex bodies, replete with inhomogeneities and internal structures that contribute to unpredictable behavior. The observation of peculiar behavior does not necessarily imply inexplicable behavior. It may simply indicate insufficient data to construct a complete model. However, the data from Meerkat reveals something further: a stable line structure across multiple observation periods. The hydroxyl absorption appeared consistent in every observation within the detection window, effectively ruling out instrumental error or transient interference. If this were a glitch, it would manifest in one scan and disappear in the next. If it were terrestrial interference, it would appear randomly, uncorrelated with the comet's position. But the signal precisely tracked Oumuamua's movement across the sky at the rate predicted by its ephemeris, exhibiting a Doppler shift precisely matching the velocity measurements required. This level of consistency strongly suggested a genuine astrophysical source, rather than an artifact. And, as is always the case, the public imagination ran wild online. SETI subreddits became abuzz with speculation. Was this first contact? Was Oumuamua a probe? Could it be transmitting on other frequencies? These questions remain to be investigated. Mainstream media outlets, to their credit, largely conveyed the story accurately. Interstellar object yields first radio detection. Hydroxyl lines confirm water breakdown on alien comet. However, as the narrative filtered through social media, it morphed into sensationalized headlines such as "Scientists detect alien transmission from interstellar visitor," which, while technically accurate if transmission is interpreted as emitted radiation and alien as originating from beyond our solar system, is profoundly misleading if taken to imply deliberate communication from extraterrestrial intelligence. Thus, our current understanding is this: 8 anomalies, one of which is a radio detection unprecedented in the annals of interstellar object studies. A celestial location that echoes one of SETI's most enduring unsolved mysteries. Chemistry that is perfectly natural, yet also perfectly aligned with the fundamental building blocks of life. And a growing realization that even if this is not evidence of aliens, even if it is merely a comet exhibiting typical cometary behavior, the implications are nearly as profound. Because if it is not aliens, then what we are witnessing is proof that the ingredients for life are transported between stars aboard cosmic vessels. And that, billions of years ago, an object much like Oumuamua may have delivered the water and organic compounds that rendered Earth habitable in the first place. Part 5 explores the implications. If there were more than just chemistry involved, let us indulge in a thought experiment for a moment. What if the hydroxyl absorption lines from Oumuamua were not purely natural? What if, embedded within that chemistry, there was something deliberate, something engineered? I am not asserting this is the case. The evidence overwhelmingly supports a natural explanation. However, scientific progress is driven by asking what if and exploring the boundaries of possibility. Therefore, let us push that boundary to see where it leads. If the absorption lines were deliberately engineered, we would be observing a form of communication operating on principles entirely alien to our current technology. Human radio transmissions are fundamentally about emission. We generate electromagnetic waves and broadcast them into space, hoping for reception by a receiver tuned to the appropriate frequency. Absorption, conversely, is a passive process. It necessitates a background radiation source and a medium that selectively attenuates specific frequencies. To engineer an absorption signal, one would need to exert extraordinary precision in controlling the chemistry of a comet or asteroid, manipulating the abundance and distribution of hydroxyl radicals to create spectral features that encode information. This is orders of magnitude more challenging than simply constructing a radio transmitter. But let us assume for a moment that it is possible. Imagine a civilization so advanced that it can imbue interstellar objects with specific chemical compounds, programmed to be released at precise rates when heated by a star. The information would not reside in the mere presence of these molecules, which are common throughout the universe, but in their timing, their spatial distribution, and their relative abundances. Perhaps the signal is not contained within a single set of hydroxyl lines, but is distributed across dozens of observations over time, a sequence that only reveals its structure when the entire perihelion passage is analyzed. Perhaps the communique is encoded within the interrelationships of various molecular entities, specifically hydroxyl and carbon monoxide alongside cyanide, all emanating in distinct sequences that collectively form mathematical constants or celestial coordinates. Such a technological signal would prove exceptionally challenging to differentiate from natural phenomena without prolonged scrutiny. Comprehensive multi-wavelength surveillance would be requisite, meticulously tracking every chemical emission and absorption signature, spanning from the ultraviolet to the radio spectrum. This would necessitate compiling an exhaustive chemical inventory over a duration of weeks or even months. Furthermore, the spectral resolution would need to be sufficiently fine to detect subtle variations in line width or intensity that might suggest deliberate modulation. Even with these stringent measures, the principle of Occam's razor would present a significant hurdle. The simplest explanation is invariably favored. A naturally occurring comet exhibiting unusual, yet physically plausible, outgassing patterns would invariably be considered a more straightforward explanation than an artificial probe masquerading as such. Consider this in contrast to prior hypotheses regarding technosignatures. Dyson spheres, Those theoretical megastructures designed to harness a star's entire energy output are predicted to emit distinctive infrared signatures as waste heat. Extensive searches for these have yielded no conclusive evidence, with all observed phenomena attributable to dust or natural stellar processes. Narrowband radio pulses, exemplified by the WOW signal, offer intriguing clues but have never been repeated, precluding confirmation of their artificial origin or categorization as rare astrophysical events. Light modulation, the concept of an extraterrestrial civilization signaling by intentionally altering their star's brightness patterns, briefly generated excitement with the case of Tabby's star. However, subsequent observations revealed mundane explanations involving dust clouds and orbiting debris. The appeal of molecular absorption as a method of communication lies in its ingenious exploitation of natural processes for concealment. If one were to design a probe intended to traverse a star system undetected, disguising it as a comet would be an inspired strategy. Comets are ubiquitous and generally disregarded unless they become sufficiently luminous to capture the attention of amateur astronomers or pose a significant impact threat. A probe camouflaged by ice and dust, releasing gases indistinguishable from a genuine comet, could conduct close-up studies of a solar system while being perceived as merely another fragment of frozen cosmic detritus. The sole potential giveaway would be subtle anomalies, the sort of fine details that only surface upon meticulous examination. These could include unexpected adjustments in trajectory, precisely calibrated chemical ratios, or patterns in the outgassing that statistical analysis identifies as non-random. However, a significant challenge arises from the energy requirements. The manipulation of chemistry at the molecular level demands extraordinary precision. Natural processes are inherently chaotic, governed by thermodynamics. To engineer ordered patterns in the release of volatile substances, active control mechanisms would need to be integrated throughout the object. This might involve nanoscale machines meticulously regulating sublimation rates, or perhaps exotic materials with engineered thermal properties that direct heat to specific regions on command. The technological sophistication required would far surpass our current capabilities, rendering the term advanced an inadequate description. We are contemplating engineering at the atomic scale across an entire object spanning hundreds of meters or kilometers, incorporating systems robust enough to withstand millions of years of interstellar radiation and extreme temperature fluctuations. If this is indeed the scenario, then the civilization responsible operates on scales we can scarcely comprehend. And yet, when we return to the empirical data, every element aligns perfectly with established cometary spectra. The ratio of the hydroxyl line, the relationship between the 1665 MHz features, precisely matches theoretical predictions for thermal excitation in a low-density gas. The line widths correspond directly to the expected velocity dispersion of molecules evaporating from a small celestial body. The Doppler shift aligns with the measured heliocentric velocity within acceptable uncertainties. There is no anomalous modulation, no hidden substructure within the spectral features, and no extraneous frequency components. If this is artificial, it is flawlessly executed, perhaps too flawlessly, which once again propels us back towards a naturalistic explanation. Public reaction has been a compelling amalgamation of enthusiasm and disappointment. The excitement stems from the possibility, however remote, of witnessing something unprecedented. The frustration arises from the likelihood that it is merely a comet, which fails to satisfy our inherent desire for a universe that is more enigmatic, more wondrous, and more populated than it appears. Social media platforms have been abuzz with variations of "It's not aliens again," and "Why is it never aliens?" a sentiment that perfectly encapsulates the prevailing cultural mood. We are a species yearning for contact, conditioned by decades of science fiction to anticipate that initial extraterrestrial signal. Consequently, every unusual celestial phenomenon ignites our hope that this will be the one. Yet, invariably, the answer returns: natural processes, the predictable march of physics, nothing extraordinary to report. However, this response might overlook a crucial aspect. Perhaps we should broaden our definition of what constitutes communication. Consider the natural world on Earth. Trees communicate through intricate fungal networks, exchanging nutrients and issuing warnings. Whales traverse ocean basins with their songs, conveying information about their location and identity. Bees perform dances to indicate the whereabouts of flower patches. None of these systems evolved with the intention of communicating with humans, yet they undeniably transmit information by encoding meaning through chemistry, physics, and observable behavior. What if the universe operates on a similar principle? Could there be natural processes that carry information across interstellar distances, patterns in molecular distribution, or the timing of stellar flares that encode something significant, not necessarily for us directly, but for any systems capable of deciphering them? From this perspective, 3I Atlas is indeed communicating. It is broadcasting its chemical composition, its thermal history, and its origin narrative, meticulously inscribed in isotopic ratios and volatile abundances. The message proclaims, "I originated in the distant reaches of another star system. I was expelled by gravitational interactions, possibly a close encounter with a giant planet or a stellar companion. I traversed the galaxy for millennia, in cold and darkness, accumulating cosmic ray exposure and interstellar dust. Now I am here, briefly illuminated by your sun, releasing the ices I have carried across light years." While this is not intelligent communication in the conventional sense, it is nonetheless information, preserved and transmitted across immense distances and vast timescales. The philosophical quandary then becomes, if nature is already replete with signals, and we are only beginning to learn how to interpret them, does the distinction between the natural and the artificial truly hold significance? Or is it merely a fallacious dichotomy imposed by our limited perspective? Perhaps intelligence is not a distinct category, but rather an emergent property of sufficiently complex chemistry. It is conceivable that the boundary between life and non-life, between signal and noise, between message and mere chemistry is far more indistinct than we are willing to acknowledge. It is possible that we have been searching for communication that mirrors our own, electromagnetic waves carrying encoded data, when the universe has been communicating all along in a language we are only just beginning to comprehend. This language is composed of molecules assembling and dissociating, of gravity sculpting orbital paths, of light transmitting information across billions of years. Thus, this thought experiment leads us to the following conclusion. The hydroxyl lines emanating from 3I Atlas are almost certainly a product of natural chemistry, nothing more. However, to dismiss it as nothing more would be to understate its profound implications. This represents a direct chemical analysis of interstellar material, the first instance of us being able to ascertain the composition of ice from another star system using radiospectroscopy. It validates the presence of water, the molecule pivotal to the emergence of life on Earth, in abundance beyond the confines of our solar system. It demonstrates that comets possess the capacity to preserve volatiles throughout the harsh environment of interstellar space. And it suggests, perhaps, that the fundamental building blocks of life are not rare cosmic coincidences but rather common cargo aboard wandering icebergs that traverse the galaxy, delivering organic chemistry wherever gravitational forces direct them. If this is not a form of communication, if this is not the universe imparting something profound about our own origins, then it is difficult to conceive of what would be. For what is yet to come may reveal that the universe is not merely speaking, but actively teaching us about our genesis. Part 6: Interstellar Visitors and the Significance of 3I Atlas. Let us broaden our perspective and contextualize 3I Atlas, as understanding its importance necessitates an appreciation of the rarity of such visitors. As of late 2025, humanity has definitively confirmed the passage of precisely 3 interstellar objects through our solar system. 3. Out of the billions of asteroids and comets catalogued over centuries of observation, only 3 have been unequivocally identified as originating from beyond our solar system. This number should be startling, not because interstellar objects are inherently scarce, but rather because it suggests a profound deficit in our observational capabilities. Simulations predict that at any given moment, numerous interstellar visitors should be traversing the inner solar system. However, they are faint, move at high velocities, and are easily mistaken for ordinary solar system debris until their orbits are calculated, revealing a hyperbolic trajectory, unbound and approaching from velocities indicative of an extrasolar origin. The inaugural confirmed visitor arrived in October 2017, designated 1/UAMUAMUA, a Hawaiian term signifying a scout or messenger. It was detected by the Pan-STARRS telescope in Hawaii as a faint point of light moving with considerable speed across the sky. Initial observations suggested a rocky asteroid, possibly 100 meters in length, rotating erratically. However, subsequent events introduced an element of peculiarity. As it swung around the Sun and commenced its departure back into interstellar space, it exhibited an acceleration, increasing its velocity beyond what could be attributed to gravity alone. While not a substantial increase, it was statistically significant. Outgassing from cometary activity could account for this, yet UAMUAMUA displayed no visible coma, no tail, and no spectroscopic evidence of volatile compounds. The source of this propulsion remained elusive. Numerous theories emerged. Perhaps it was a hydrogen iceberg that sublimated without leaving discernible traces. Alternatively, it could have been a solar sail, a wafer-thin reflective membrane propelled by solar radiation pressure. Speculation also arose regarding its shape, with theories proposing a pancake-like or cigar-like form, geometries that would experience anomalous radiation forces. We will likely never know for certain. It has long since departed, receding into the darkness at 26 kilometers per second, and our initial detection was not early enough to acquire the necessary observations. The second object, I/Borisov, appeared in August 2019. It was discovered by Gennady Borisov, an amateur astronomer utilizing a homemade telescope in Crimea. In stark contrast to UAMUAMUA, Borisov exhibited behavior entirely consistent with that of a comet. It possessed a coma and a tail. Spectroscopic analysis revealed the presence of water vapor, carbon monoxide, and cyanide, all characteristic of a snowball heated by the sun. Its orbit was unequivocally hyperbolic, indicating an origin in interstellar space at a velocity of 32 kilometers per second. This meant it was not merely passing through, but was hurtling through our system, decelerating only minimally as it completed its trajectory around the Sun. Observations indicated a nucleus approximately half a kilometer in diameter, composed of ices similar to those found in comets formed within our own solar system, suggesting that the processes of comet formation might be universal. In a sense, it was disappointingly unremarkable, precisely the type of object one would anticipate if a comet were ejected from the outer reaches of any planetary system. There were no anomalies, no enigmas, only confirmation that cometary chemistry operates uniformly across the cosmos. And now, we have 3I Atlas, designated C/2025 and 1, detected by the Atlas survey in July 2025. Its hyperbolic orbit was confirmed within a matter of weeks, revealing an inbound velocity of 42 kilometers per second relative to the Sun. This speed is such that no gravitational interaction within our solar system could have accelerated it to this magnitude. It unequivocally originated from beyond our solar system. However, Unlike the straightforward cometary behavior of Borisov and the perplexing acceleration of UAMUA, Atlas occupies an intriguing intermediate position. It exhibits cometary activity, with a coma and the release of hydroxyl lines that we have been discussing. Yet, it also displays anomalies in its brightness, the dynamics of its tail, and its rotational state, features that do not readily conform to standard models. Furthermore, it has now yielded the first radio detection ever recorded from an interstellar object, a milestone that elevates it from a mere curiosity to a discovery of historical significance. The trajectory itself is noteworthy. Atlas approached inbound almost parallel to the orbital plane of Earth and the other planets. This is unusual. Random interstellar objects are expected to approach from all directions, reflecting the three-dimensional structure of the galaxy. Objects originating from the galactic disk should cluster near the ecliptic, while those from the halo, the diffuse cloud of stars surrounding the Milky Way, should approach from steep angles, descending from above or ascending from below the plane. Atlas's near-ecliptic approach suggests it might have originated from a star system whose orbital plane coincidentally aligns with ours. Alternatively, it could be a statistical anomaly, the kind of occurrence that arises when one possesses only 3 data points. With such a limited sample size, every observation carries considerable weight, and it is not yet possible to distinguish genuine patterns from random noise. However, let us address what makes this detection historically unique. Radio observations of comets are not a new phenomenon. We have been studying hydroxyl emission and absorption from solar system comets since the 1960s, employing the same techniques that detected the signal from Atlas. What is novel is the source, an object that formed around another star, carrying ices and organic compounds that coalesced within an alien protoplanetary disk, now passing sufficiently close to our Sun for us to analyze its chemistry in real time. This constitutes direct sampling of extrasolar material without the necessity of dispatching a probe for collection. The comet has journeyed to us, and all that was required of us was to direct our telescopes toward it and listen. Radio absorption studies offer an unparalleled insight into chemistry that other techniques cannot match. Optical spectroscopy reveals reflected sunlight, which is contingent on surface composition and geometry. Infrared observations disclose thermal emission, providing information about temperature, but not necessarily about the chemical constituents. Ultraviolet spectroscopy can detect electronic transitions in molecules such as oxygen and carbon monoxide, but it is susceptible to solar contamination and atmospheric absorption. Radio spectroscopy, particularly in the L-band around 1.4 GHz, effectively cuts through most of this interference. The hydroxyl lines are clear, unambiguous, and directly correlated with water abundance. If the objective is to ascertain the water content of a comet, radio observation often represents the most effective method. The reality is that most interstellar objects pass entirely unnoticed. They are faint, move at high speeds, do not approach the Sun closely enough to become significantly luminous, or arrive from directions that render them poorly positioned for observation from Earth. The fact that we have confirmed only 3 in 8 years does not imply that only 3 have traversed our solar system. It signifies that only 3 have been sufficiently bright, slow-moving, and advantageously positioned for us to detect and characterize them before they receded back into the darkness. How many have eluded our detection? Potentially dozens, even hundreds. The precise number hinges on models of galactic stellar populations and planetary system architectures, but estimates suggest we should be detecting a handful annually with our current survey capabilities. The discrepancy between this expectation and our actual detection rate highlights the inherent challenges of interstellar object astronomy. One must be observing the correct location at the opportune moment, and even then, one must recognize what is being observed before the object moves beyond our observational window. Now, let us engage in a moment of speculation. What if these objects serve as a natural delivery system for organic compounds? Stars continuously eject comets and asteroids. Gravitational interactions during planetary formation scatter smaller bodies into interstellar space. Some estimates propose that the Milky Way harbors trillions of rogue comets drifting between stars, too dim to be observed, yet collectively representing an immense reservoir of ice and organic material. If even a minuscule fraction of these objects contain prebiotic molecules, such as amino acids or nucleobases, the chemical precursors to life, then interstellar space is far from devoid. It is replete with chemistry, subtly intermingling and redistributing material between stellar systems over timescales of millions of years. It is conceivable that Earth received its water and organic compounds through precisely this process. Interstellar visitors colliding with a nascent planet, depositing volatiles that ultimately coalesced into oceans and initiated biological processes. This represents the most conservative interpretation of the panspermia hypothesis, not that life itself migrates between stars, but that the essential ingredients for life do. 3I Atlas, with its hydroxyl signature confirming water dissociation and its trajectory substantiating extrasolar origin, lends credence to this concept. It serves as a data point, among the earliest, demonstrating that the chemistry essential for life is not confined to individual star systems. It migrates, it disseminates, and given sufficient time, given billions of years and countless collisions, it has the potential to seed habitable worlds throughout the galaxy. This prompts a critical question. If the building blocks of life are widespread and mobile, why does life itself appear to be so rare? Or is it truly rare? Perhaps we simply lack the means to recognize it yet. Or perhaps we are alone, not due to a deficiency in the fundamental chemistry, but because the spark that transforms chemistry into biology is an event of vanishing low probability, a statistical miracle that has occurred only once within the observable universe. However, I am preempting the narrative. The immediate implication of the 3I Atlas detection is more straightforward. We can now employ radio spectroscopy to study interstellar material, thereby augmenting the arsenal of planetary astronomy with a powerful new instrument. The subsequent visitor might possess an even richer volatile content, approach closer, appear brighter, and be better positioned for comprehensive multi-wavelength follow-up observations. We are entering an era where the study of interstellar objects is transitioning from opportunistic observations to systematic investigation. The chemical insights we acquire will undoubtedly reshape our understanding of planetary system formation, not only within our own solar system, but across the cosmos. For if Atlas carried water and organic compounds across light years, then every other ejected comet likely does the same. The galaxy is thus crisscrossed with invisible highways of chemistry, awaiting discovery and mapping. Part 7. Chemistry, Physics, and the Volatile Budget of an Interstellar Object. To precisely understand the hydroxyl detection, it is imperative to comprehend the physics governing volatile sublimation, the process by which frozen ice is transformed directly into gas without passing through a liquid phase. This is the identical mechanism that causes dry ice, solid carbon dioxide, to appear to smoke when exposed to ambient temperature. Heat permeates the solid, disrupting the molecular bonds that maintain the crystalline structure, allowing molecules to escape into the surrounding space. For water ice, this process becomes efficient at temperatures exceeding 170 Kelvin, with the rate increasing exponentially as the temperature rises. At 230 Kelvin, the estimated surface temperature of Atlas at the time of the detection, water sublimation occurs vigorously, releasing gas at rates sufficient to sustain a visible coma and tail. The Swift UV telescope corroborated these water sublimation signatures weeks prior to the radio detection. Swift specializes in ultraviolet spectroscopy, identifying the electronic transitions of molecules as they fluoresce under solar radiation. Hydroxyl, in particular, exhibits strong UV emission lines that manifest when molecules absorb sunlight and re-emit it at characteristic wavelengths. Swift detected these lines, quantified their intensity, and calculated a water production rate on the order of 10 to the power of 27 molecules per second. While this represents a substantial quantity, it is actually modest for a comet in proximity to its perihelion. Larger comets can discharge 10 to the power of 29 or even 10 to the power of 30 molecules per second at their peak activity. Atlas, measuring a few hundred meters in diameter, exhibits a modest yet significant energetic output. This output is sufficient to generate a discernible hydroxyl cloud that stretches for thousands of kilometers from its core. The process begins when solar ultraviolet photons interact with water molecules in the comet's coma. These photons possess enough energy to sever the hydrogen-oxygen bonds within H2O, splitting it into hydroxyl, OH, and atomic hydrogen, H. This phenomenon, known as photodissociation, occurs within hours to days, contingent upon the intensity of the ultraviolet radiation. The lightweight hydrogen atoms rapidly dissipate, diffusing out of the coma and eventually merging with the solar wind. Hydroxyl molecules persist for a longer duration, approximately 100,000 seconds, before either undergoing further photodissociation into oxygen and hydrogen or colliding with other molecules. Throughout their existence, these OH molecules absorb radio waves at their characteristic frequencies, generating the absorption lines that the Meerkat telescope detected. The intensity of these lines is directly correlated with the column density of hydroxyl along the line of sight, which in turn depends on the rate of water production and the observation geometry. This observation can be contrasted with 2I/Borisov, which also displayed hydroxyl emissions during its passage in 2019. Borisov's OH lines were identified by multiple radio observatories, including the IRM 30-meter telescope in Spain and the Nankai radio telescope in France. However, Borisov's hydroxyl signal was less pronounced, indicating a lower rate of water production relative to Atlas, despite Borisov being physically larger. The disparity arises from compositional differences. Comets are not uniformly constituted. Some possess a greater abundance of water ice, while others contain more carbon dioxide, carbon monoxide, or unusual volatiles such as methane and ammonia. Atlas appears to be exceptionally rich in water, possibly due to its formation in a region of its parent protoplanetary disk where water ice was plentiful, or because it shed other volatiles over millions of years of interstellar exposure, leaving water as the predominant remaining component. The thermal environment, at 230 Kelvin, is crucial to this understanding. At this temperature, water ice readily sublimates, while more volatile species, like carbon monoxide, which sublimes at temperatures as low as 30 Kelvin, have likely long since departed. If Atlas has traversed interstellar space for millions of years, exposed to cosmic rays and the faint galactic background radiation, any highly volatile ices on its surface would have gradually sublimated over time. What remains is primarily water ice, potentially intermixed with refractory organic compounds that do not easily sublimate, forming a dirty snowball that preferentially releases water as it warms. This selective loss of volatiles offers one explanation for why interstellar comets might differ from those originating within our solar system, even if their formation processes were similar. Now, let us consider sublimation rates and the role of pressure. Sublimation is influenced not only by temperature, but also by the equilibrium between vapor pressure and ambient pressure. In the near vacuum of space, the ambient pressure is effectively zero, meaning that even minimal heating can induce rapid sublimation. However, if gas is released with sufficient speed, it generates its own localized pressure, forming a tenuous atmosphere around the nucleus that can decelerate further sublimation. This self-regulating mechanism explains why comets do not instantaneously disintegrate upon approaching the Sun. The escaping gas creates a buffer layer that moderates heating, enabling sublimation to proceed at a consistent pace rather than occurring all at once. For Atlas, the estimated gas production rate suggests a surface pressure within the coma of approximately 10 to the power of -6 millibars, which is 1 trillion times less than Earth's atmosphere, yet substantial enough to impact the thermal balance. The implications for planetary formation models are significant. If interstellar comets can preserve water ice over timescales of millions of years, it offers insights into the stability of ices under the cold, dark conditions prevalent between stars. It suggests that bodies rich in volatiles can endure ejection from their parent systems, maintain their chemical integrity during interstellar journeys, and deliver these volatiles intact to any planetary system they encounter. This supports models of planetary system formation that incorporate late-stage volatile delivery, the concept that rocky planets, like Earth, might initially form without water and subsequently acquire it, and organic compounds through comet impacts during the final phases of accretion. If interstellar comets can contribute to this process by delivering extraterrestrial water to nascent planets, then the chemical composition of any given world could represent a blend of local and imported materials, a mixture obscured by billions of years of cosmic transit. This brings us back to panspermia, one of the most enduring and contentious hypotheses in astrobiology. The term literally signifies seeds everywhere. It proposes that life, or at least the precursors to life, could propagate between planets or even star systems via comets and asteroids. The more conservative interpretation, sometimes termed pseudopanspermia, posits that organic molecules, the fundamental constituents of life, are transported on these celestial bodies and provide sterile worlds with the requisite chemistry for biology to arise independently. The radical version suggests that life itself, in the form of dormant microorganisms, could survive such journeys and establish colonies on new planets. Most scientists remain skeptical of the radical version due to the harshness of space. Radiation, vacuum, and extreme temperatures all militate against the survival of even robust microbes. However, the conservative interpretation is entirely plausible. Organic molecules exhibit considerable resilience and can withstand radiation doses that would sterilize a planet's surface. Experiments have demonstrated that amino acids and nucleobases, essential components of proteins and DNA, can form within icy mantles under radiation conditions analogous to those found in interstellar space. Laboratory simulations have directly tested this. Researchers combine mixtures of water ice, methanol, ammonia, and carbon monoxide, freeze them onto surfaces at temperatures around 10 Kelvin, and bombard them with ultraviolet light or high-energy particles to replicate cosmic rays. The outcome is complex organic chemistry, including the synthesis of amino acids like glycine and alanine, the simplest protein building blocks. If such chemistry occurs in a laboratory setting, it almost certainly transpires in space on the surfaces of comets and dust grains traversing molecular clouds. Consequently, every interstellar object, such as Atlas, potentially carries a repository of prebiotic molecules, a chemical toolkit capable of initiating biological processes on any world where conditions are conducive. The detection of hydroxyl from Atlas corroborates that even interstellar material, which has been adrift in the galaxy for an indeterminate period, can retain complex molecules. Water not only survives interstellar transit, but persists in a sufficiently intact state to sublimate and produce detectable chemical signatures upon heating. This finding is profound. It signifies that the cosmic chemical inventory is not static, confined to individual star systems, but is dynamic, continuously redistributed by gravitational interactions and stellar encounters, with comets and asteroids serving as delivery mechanisms. The ingredients for life are not rare or exclusive. They are common, mobile, and likely dispersed throughout the galaxy on countless icy bodies that remain unseen. Atlas simply represents one such body that we have had the opportunity to observe in action. Part 8. Trajectory Oddities and the Maneuvering Hypothesis. Now, let us examine the orbit itself. While the chemical composition of 3I/Atlas raises questions, its trajectory further fuels speculative discourse. The object's path through the solar system is hyperbolic, as expected for an interstellar visitor, but its specific geometric configuration warrants scrutiny. Atlas approached nearly precisely along the ecliptic plane, the flattened disk defined by Earth's orbital path around the Sun. Most solar system bodies tend to cluster near this plane, having formed from the same rotating disk of gas and dust that coalesced to create the Sun and planets some 4.6 billion years ago. However, interstellar objects originate elsewhere. They should arrive from random directions, reflecting the three-dimensional distribution of stars in the galaxy. Yet, Atlas entered the solar system on a flat trajectory, as if deliberately targeting the inner solar system where planets are densely packed. NASA's Anomaly Report, compiled from observations spanning September through October, noted minor deviations in the predicted trajectory. These variations were small enough to potentially be attributed to asymmetric outgassing. When a comet releases gas, this gas carries momentum. If the outgassing is more intense on one side of the nucleus than the other, perhaps due to one hemisphere being more volatile-rich or receiving more direct illumination, the result is a net thrust that subtly alters the comet's course. This phenomenon is known as a non-gravitational force, and is well documented for solar system comets. For instance, Halley's Comet returns to the inner solar system a few days earlier or later than purely gravitational calculations predict, owing to rocket effects from sublimation either propelling it forward or retarding it, depending on the orientation of the nucleus. However, some observers have asserted that the deviations in Atlas's orbit appear too systematic, too coordinated, to be attributed to random outgassing. They cite the formation of both a tail and an antitail as evidence of controlled propulsion. This would involve symmetrical jets expelling material in opposite directions, allowing for precise adjustments to the trajectory. The New York Post, never one to shy away from sensational headlines, published articles speculating on the comet's maneuvering through the solar system, complete with artistic renderings of a sleek probe encased in ice. The premise is that if one were to construct an interstellar spacecraft and wish to evade detection, one would cloak it in cometary material, utilize sublimation for propulsion, and navigate using precisely controlled gas jets. From a distance, it would appear as a comet, with only a detailed analysis of its trajectory revealing its true nature. To be clear, this is highly speculative, bordering on fantasy, yet it is not entirely without a basis in physical principles. The concept of using outgassing for propulsion is physically sound. Indeed, proposals for interstellar probes have advocated precisely this approach, encasing a spacecraft in frozen hydrogen or water and harnessing the expanding gas as propellant upon solar heating. While less efficient than chemical rockets or ion drives, it is simple, requires no onboard power, and renders the spacecraft virtually indistinguishable from a natural comet until subjected to close scrutiny of its trajectory. The Breakthrough Starshot project, which aims to dispatch minuscule laser-propelled probes to Alpha Centauri, has explored hybrid designs incorporating light sails with volatile coatings for precisely this reason. The formation of an antitail introduces further complexity. Antitails can arise naturally as perspective effects, but the observed symmetry in Atlas is striking. The main tail and antitail appeared roughly equal in brightness and length, suggesting that dust was ejected in two opposing directions with comparable force. This is difficult to explain through simple rotational outgassing unless the nucleus possesses active regions at opposite poles, expelling jets aligned with the rotational axis. If the nucleus spins sufficiently rapidly, and these polar jets are potent enough, such symmetry could be produced. However, This necessitates a specific configuration, active regions at both poles, which is not guaranteed by any current models of cometary structure. The timing of events adds another layer of intrigue. Atlas reached perihelion, its closest approach to the Sun, on October 29, 2025, at a distance of approximately 0.66 astronomical units from the Sun, roughly two-thirds the distance between Earth and the Sun. This proximity provides significant solar heating, but is not so close that the comet would be disintegrated by tidal forces. More notably, perihelion occurred near what orbital mechanics specialists refer to as an orbital maneuver window, a point in an orbit where a small change in velocity has the maximum impact on the final trajectory. If one intended to adjust a path to target a specific destination after departing the solar system, perihelion would represent the optimal juncture for such an adjustment. One would wait until moving at maximum velocity deep within the Sun's gravitational well, then apply thrust to alter direction with peak efficiency. The circumstance of Atlas passing through this window with trajectory deviations, however minor, has fueled speculation that its path was, or is being, guided. However, let us apply a healthy dose of skepticism. Thermal models of cometary outgassing can account for trajectory deviations without recourse to propulsion. When one side of a comet heats up more rapidly than the other, perhaps due to its rotational axis being tilted relative to the Sun, that side sublimes more gas, generating thrust. This results in a torque that can either accelerate or decelerate the nucleus's spin, and a force that subtly nudges the trajectory. These effects are subtle but measurable, and have been observed in every well-studied comet within our solar system. There is no direct evidence of propulsion systems, no anomalous accelerations that defy explanation by standard physics, and no spectroscopic signatures of exotic chemistry suggesting artificial control over outgassing. Nevertheless, the question persists: if it were artificial, how would we know? If an advanced civilization sought to dispatch probes to other star systems, and if they acted judiciously, those probes would likely resemble natural objects. They would employ gravity assists, solar flybys, and chemical releases designed to mimic cometary behavior. The only potential giveaway might be statistical patterns in trajectories, such as clustering around specific star types, perihelion distances optimized for observational geometry, or chemical signatures too consistent or precisely timed to be naturally occurring. With a sample size of only 3 confirmed interstellar objects, we are far from being able to discern such patterns. We require hundreds, even thousands, of detections before we can differentiate between natural visitors and hypothetical probes disguised as comets. So, here is our conclusion on the maneuvering hypothesis. It is theoretically possible, unsupported by current evidence, and almost certainly unnecessary to explain the observed phenomena. Atlas is indeed exhibiting unusual behavior, but comets are inherently chaotic bodies. Their rotational states, thermal properties, and outgassing patterns are dependent on internal structures that we cannot directly observe. Minor compositional inhomogeneities can lead to substantial variations in behavior. The trajectory deviations are real but fall within the range of what asymmetric outgassing can produce. The timing of perihelion near an orbital maneuver window is coincidental, as every orbit possesses a perihelion, and every perihelion is theoretically optimal for trajectory modifications. When examining patterns with a small sample size, one is likely to find them regardless of their intrinsic significance. However, I shall leave you with this thought: what if coincidences are not random? What if the universe, in its immense complexity, occasionally generates patterns that appear designed even when they are not? And what if embedded within those patterns lies information that we have yet to decipher? Because whether Atlas is maneuvering or simply tumbling through space governed by the impersonal laws of physics, its trajectory has brought it to us, close enough for study, bright enough for detection, and timed with remarkable precision to produce a historically significant radio signature. coincidence, or deliberate choreography? The available data does not provide an answer to this question. Not yet. Part 9. SETI. Radio telescopes and a new detection frontier. Traditional SETI, the search for extraterrestrial intelligence, has historically focused on a single objective: narrowband beacons. The underlying logic is straightforward. Natural astrophysical sources emit radiation across a wide spectrum of frequencies. Stars, for instance, radiate across the entire electromagnetic spectrum, from gamma rays to radio waves. Pulsars produce broadband pulses. Supernova remnants glow across all wavelengths simultaneously. However, a deliberate transmission from an intelligent civilization would differ. It would be spectrally pure, concentrated at a single frequency or a narrow band of frequencies, as this represents the most efficient method of encoding information within limited power. If one is broadcasting across the galaxy and aims for detectability, energy is not wasted by spreading it across the entire spectrum. Instead, a specific frequency is chosen, likely something significant, such as the hydrogen line at 1420.406 MHz, and all power is directed into that channel. The result is a sharp spike in the spectrum, a signal so narrow it cannot be mistaken for natural phenomena. This is what SETI endeavors to detect. Enormous radio telescopes, such as the Green Bank Telescope in West Virginia, the 500-meter aperture spherical telescope, FAST, in China, and the Very Large Array in New Mexico, dedicate thousands of hours to scanning the sky in search of narrowband signals that exhibit repetition, structure, and the unmistakable hallmark of intentionality. This endeavor began with Frank Drake's Project Ozma in 1960, when he aimed a radio dish at Tau Ceti and Epsilon Eridani and listened for 6 months. He detected nothing. 65 years later, despite advancements in sensitivity that would have seemed miraculous to Drake, we still hear nothing. No repeating beacons, no modulated transmissions, no alien encyclopedias beamed our way, only the vast, silent void of the cosmos. The detection of hydroxyl from 3I/Atlas necessitates a paradigm shift in our understanding of technosignatures. What if we have been searching for the wrong type of signal all along? What if intelligence does not always broadcast intentionally? What if the signatures of advanced technology are subtle, embedded within chemical compositions or orbital dynamics, indistinguishable from natural processes unless one knows precisely what to look for? This concept pertains to non-intentional technosignatures, industrial byproducts, or engineering artifacts that leak detectable radiation, not by design, but as an inevitable consequence of large-scale technological operation. Consider Earth as an example. We have been emitting radio signals into space for over a century, ever since Marconi transmitted his first wireless message. Television broadcasts, radar installations, satellite communications, all of these radiate outward at the speed of light, creating an expanding sphere of electromagnetic noise that currently extends approximately 100 light-years in every direction. If an alien civilization were to point a sensitive radio telescope at our solar system from a nearby star, they might not necessarily detect a deliberate beacon. Instead, they would observe chaos, thousands of overlapping frequencies modulated in ways that reflect our technology, our entertainment, and our military communications. It would be a jumbled signal, yet unmistakably artificial. This constitutes a non-intentional technosignature and is likely far more prevalent than deliberate SETI beacons, if only because most civilizations probably do not seek to announce their presence to the galaxy. Now, apply this logic to chemistry. An advanced civilization capable of constructing starships or manipulating comets would inevitably leave chemical imprints. This could include exhaust fumes from propulsion systems, unusual isotopic ratios resulting from material refinement or nuclear reactions, or molecular abundances deviating from equilibrium chemistry due to active control of outgassing or atmospheric composition. These would not be messages but rather fingerprints, traces left by technology operating within observable environments. The sole method for their detection is spectroscopy, the same technique employed to detect hydroxyl in 3I/Atlas. The Meerkat array is uniquely positioned to pioneer this type of detection. Its 64 dishes spread across 8 kilometers of the Kara Desert in South Africa create an interferometer with exceptional sensitivity in the L-band, the radio frequency range from 1 to 2 GHz. This is the frequency range where hydroxyl resides, alongside dozens of other molecules vital for astrochemistry. The Meerkat Observatory is capable of simultaneously examining numerous frequency bands, diligently searching for both emission and absorption signatures originating from water, carbon monoxide, formaldehyde, and methanol. These are precisely the complex organic molecules typically found in regions of active star formation and, as it turns out, potentially on interstellar comets. The correlator, essentially a supercomputer tasked with amalgamating the signals from all 64 of the telescope's dishes, processes an astonishing quantity of data, several petabytes daily, identifying significant spectral features in near real time. A crucial aspect of this process is the elimination of interference originating from Earth, a task at which Meerkat excels. The Kara region, where Meerkat is situated, is renowned as one of the most radio-quiet locations on the planet, specifically protected by South African legislation against radio frequency pollution. This means there are no cellular towers, Wi-Fi routers, or broadcast transmitters within hundreds of kilometers. Any minor sources of interference that do exist, such as passing satellites or distant radar installations, have predictable frequencies and can be identified and filtered out during the data analysis phase. The detection of hydroxyl from the Comet 3I/2023 A3 successfully passed all interference checks. The signal was only observed when the telescope was precisely aimed at the comet's predicted position in the sky. Furthermore, it consistently tracked the object's movement, exhibiting a Doppler shift precisely matching the velocity measurements required. The signal vanished when the observation window concluded, consistent with the comet passing behind the Sun from Earth's vantage point. This sequence of events significantly bolsters the credibility of the detection. Systematics, those inherent, systematic errors that inevitably plague any scientific measurement, are the nemesis of radio astronomy. Sidelobe leakage, where the telescope inadvertently picks up signals from directions other than its intended target, can lead to spurious detections. Atmospheric absorption, particularly from water vapor in Earth's atmosphere, can distort spectra, creating artificial features. Calibration errors, occurring when the instrument is not perfectly tuned, can introduce noise that mimics a genuine signal. Meerkat's rigorous data integrity checks are specifically engineered to identify and mitigate all these issues, and the 3I/2023 A3 detection passed every single test. The hydroxyl lines appeared with the correct spectral shape, the precise frequency, and the expected intensity. This was not an artifact. It was a genuine observation. Efforts are currently underway to replicate this detection. The Green Bank Telescope, a massive 100-meter single-dish instrument located in West Virginia, stands as one of the most sensitive radio telescopes on Earth, capable of registering signals far fainter than Meerkat's detection threshold. The 500-meter aperture spherical telescope, FAST, in China, boasting an even larger collecting area with its 500-meter dish, could potentially detect hydroxyl lines from 3I/2023 A3 if the geometric alignment permits observation. The Very Large Array, VLA, in New Mexico, with its 27 dishes spread across the desert landscape, offers a different type of sensitivity, proving more adept at filtering out discrete point sources and isolating the diffuse emission emanating from a comet's coma. If all three of these powerful instruments independently confirm the hydroxyl signature, it would effectively dispel any lingering uncertainty regarding the detection's authenticity. However, a significant complication arises. 3I/2023A3 Such an atlas is a variable object. Two earlier observation attempts, conducted on September 20th and 28th, yielded no results. There was no detection of hydroxyl or any other molecular lines, only background noise. This observation strongly suggests that the signal is transient, manifesting only under specific conditions. It is plausible that the comet needs to reach a particular temperature threshold before sufficient water sublimation occurs to produce detectable hydroxyl. Alternatively, the viewing geometry may play a role, with hydroxyl clouds potentially being concentrated in specific directions relative to the nucleus. Another possibility is the rotation of the nucleus, which could periodically expose volatile-rich regions to sunlight, leading to bursts of outgassing that subsequently fade as those regions move back into shadow. Without continuous monitoring, definitively determining the cause remains impossible. This situation raises a more profound question, one that strikes at the very heart of SETI philosophy. If extraterrestrial technology were to mimic natural chemical processes, how would we ever differentiate them? Consider a scenario where an advanced civilization has mastered nanotechnology, enabling them to construct machines at the molecular level capable of controlling chemical reactions with atomic precision. Such a civilization could synthesize molecules, release them in deliberate patterns, and generate spectral signatures that appear entirely natural but subtly encode information. This encoded information could be conveyed through variations in isotopic ratios, the timing of release events, or correlations between different molecular species. Without prior knowledge of precisely what to look for, or possessing a comprehensive library of natural spectra for comparison, coupled with an algorithm sophisticated enough to detect statistical anomalies, identification would be impossible. The signal would remain hidden in plain sight, camouflaged as natural chemistry. This is the central challenge facing the search for technosignatures in the 21st century. While our instruments are becoming increasingly sensitive, allowing us to detect faint signals and even individual molecules on comets millions of kilometers away, our capacity to interpret these signals, to distinguish between natural complexity and engineered patterns, lags significantly behind. We require larger datasets, more detections, and sophisticated machine learning algorithms trained on extensive databases encompassing both natural and hypothetical artificial spectra. Our approach to SETI needs to evolve beyond a binary framework of either detecting a beacon or not. Instead, we should conceptualize it as a continuum, a spectrum of signals ranging from undeniably natural to ambiguously structured, and ultimately, to unequivocally artificial. The detection from 3I/2023A3, such an atlas, occupies a position in the middle of this spectrum. It is sufficiently natural to be explained by established physics, yet its unusual characteristics provoke further inquiry. Therefore, our current understanding is this: Meerkat has detected hydroxyl from an interstellar comet, a groundbreaking achievement in the history of radio astronomy. While the signal is consistent with natural chemistry, specifically the breakdown of water under solar radiation, it also signifies our burgeoning capability to probe the composition of extrasolar material in real time. These techniques hold the potential to detect non-intentional technosignatures, should they exist. The next interstellar visitor might be rich in complex organic compounds, exhibiting a spectrum with numerous molecular lines. Alternatively, it could display isotopic ratios inconsistent with stellar nucleosynthesis models, or release gases in patterns too regular to be attributed to thermal chaos. We will only discover this by actively searching. And our search will be limited unless we develop the necessary instruments and analytical frameworks to interpret our findings. Because even if the comet's composition is entirely natural, Even if every interstellar object we detect proves to be merely a comet, the implications remain extraordinary. The universe is teeming with chemistry, and we are finally developing the means to listen. Part 10. Broader Implications: Life, Technology, and Interstellar Visitors. Let us take a step back and consider the philosophical question that underpins this entire discussion. What if the boundaries between the natural and the intelligent are far more blurred than we have traditionally acknowledged? For centuries, we have erected a conceptual barrier between the natural world, governed by the immutable laws of physics and chemistry, and the artificial, driven by intent and design. However, this distinction might be an illusion, a product of our limited perspective. It is conceivable that intelligence is not an entity separate from nature, but rather an emergent property of it, a manifestation of the universe's inherent tendency to self-organize into increasingly complex structures. If this is the case, then the line between a naturally occurring comet and a hypothetical artificial probe becomes indistinct, as both would ultimately be expressions of the same fundamental physical laws. If the hydroxyl detection from 3I/2023A3 such an atlas is indeed natural, as it almost certainly is, then we are witnessing proof that interstellar ices can serve as conduits for the fundamental building blocks of life, traversing vast expanses of empty space over light years. Water, the universal solvent, and the molecule essential for Earth's oceans, our very blood, and every living cell on this planet, is demonstrably abundant on objects originating from other star systems. It condenses onto dust grains within protoplanetary disks, becomes integrated into comets and asteroids during planetary formation, and can be ejected into interstellar space through gravitational interactions. Once ejected, these icy bodies embark on journeys spanning millions, perhaps billions, of years, exposed to cosmic rays and starlight, yet remaining cold enough for their volatile compounds to stay frozen. Should these objects encounter another star system, their gravitational pull drawing them inward, they will heat up, release their trapped volatiles, and deliver their payload of water and organic matter to any nascent worlds present. This scenario aligns with the most defensible interpretation of panspermia, not the audacious claim of living organisms journeying between stars, but the more conservative assertion that the raw chemical ingredients for life are transported. Life, as we understand it, requires specific components: liquid water, organic molecules, and energy sources. The first two can be delivered by comets. The third is readily available on any planet situated close enough to a star to sustain liquid water on its surface. When these three elements converge in a suitable environment, biology may arise not through external intervention, but because chemistry, given sufficient time and the appropriate conditions, naturally tends toward complexity. Amino acids form spontaneously under certain environmental conditions. Lipid membranes exhibit self-assembly. RNA molecules possess the capacity for self-replication. Life, therefore, might not be a miraculous occurrence, but an inevitability, a predictable outcome of chemical processes unfolding on planetary surfaces where conditions are conducive. But if this is the case, why does the galaxy appear so silent? This is the essence of the Fermi paradox, the profound discrepancy between the high statistical probability of extraterrestrial civilizations, given the sheer number of stars and planets, and the complete absence of empirical evidence for their existence. If the ingredients for life are ubiquitous, and if chemistry inherently drives toward complexity, one would anticipate the emergence of biology on countless worlds. And if biology is common, intelligence should arise on some of these worlds, perhaps rarely, but with hundreds of billions of stars in the Milky Way alone, even a minuscule fraction should result in millions of technological civilizations. Yet, where are they? Why have we not detected their signals, their megastructures, or their probes exploring the galaxy? Perhaps the answer is far simpler than we imagine. It's possible that intelligence is common, but the sheer difficulty and energy cost of interstellar communication render it impractical for most civilizations, leading them to forego broadcasting. They might exist on their home worlds, building their societies, but without any compelling reason to transmit signals across the vast cosmic distances. Another possibility is that intelligence, while common, is inherently short-lived. Civilizations may arise and collapse on timescales of mere thousands of years, brief flickers in cosmic time that rarely coincide. Or perhaps our search methodologies are flawed. We might be seeking radio beacons when the true signals are encoded in chemical compositions, orbital mechanics, or phenomena that we have yet to even conceptualize. A more unsettling possibility, one that keeps astrobiologists awake at night, is that Earth is unique. While the chemical precursors for life might be common, the crucial spark that ignites biological evolution might be exceptionally rare. The emergence of life might necessitate not just the right ingredients, but an improbable sequence of events: the presence of a planet in the optimal habitable zone around a suitable star, a large moon to stabilize its rotational axis, plate tectonics to facilitate carbon recycling, a magnetic field to shield against harmful radiation, and a gas giant like Jupiter in the outer solar system to deflect potentially civilization-ending comets and asteroids. When one stacks enough of these individually probable yet collectively rare conditions, a filter emerges, an explanation for why life exists here but is undetectable elsewhere. However, let us return our focus to 3I/2023A3, Suchinchen Atlas, and the lessons it imparts. The detection of hydroxyl, irrespective of whether its origin is natural or hypothetically artificial, unequivocally demonstrates our capability to analyze the chemical composition of extrasolar material through spectroscopy. This represents a paradigm shift in planetary science. Prior to this advancement, our understanding of planets and comets beyond our solar system was derived from indirect methods: transit spectroscopy of exoplanet atmospheres, infrared observations of dusty disks, and computational simulations extrapolating from local knowledge. However, 3I/2023A3, Suchinchen Atlas, provided us with a tangible sample, albeit not physically collected, but close enough for our instruments to perform real-time analysis of its volatile compounds. This constitutes direct sampling without the necessity of a physical spacecraft. This breakthrough unlocks possibilities that we are only just beginning to explore. Connecting this to broader scientific endeavors, the James Webb Space Telescope, JWST, is revolutionizing exoplanet science by meticulously mapping atmospheric compositions with unprecedented detail. The Vera C. Rubin Observatory, which we will discuss at a later juncture, is poised to discover interstellar objects months before they reach perihelion, affording us ample time to coordinate multi-wavelength observations. Missions such as JWST, Rubin, and radio arrays like Meerkat and ALMA collectively form a network of instruments capable of dissecting the cosmos's chemistry across all scales, from individual molecules on comet nuclei to the atmospheric composition of planets located hundreds of light-years away. Each new detection refines our understanding of the prevalence of life's essential ingredients. The accumulating evidence increasingly suggests that these ingredients are ubiquitous. Water has been detected on exoplanets, within protoplanetary disks, in the atmospheres of hot Jupiters, and in the icy moons of our own solar system. Organic molecules, including complex carbon-based compounds and even amino acids, have been identified in meteorites, interstellar clouds, and comets. The fundamental building blocks are widespread, and chemistry operates universally according to the same laws of physics and thermodynamics across the cosmos. Given the right conditions, liquid water in contact with organic molecules and a reliable energy source, chemistry begins to exhibit fascinating behaviors. It polymerizes, it forms structures, and it initiates, albeit tentatively, the lengthy journey toward what we might define as life. And here lies a chilling thought. Perhaps intelligence is not endeavoring to communicate with us because it has already permeated the galaxy in a form we fail to recognize. Rather than distinct alien civilizations broadcasting from distant worlds, perhaps intelligence exists as a distributed phenomenon, as chemistry itself. Self-organizing patterns embedded within comets and asteroids could be transmitting information across interstellar distances through mechanisms we are only beginning to comprehend. The messages might not be encoded in radio waves, but rather in isotopic ratios, molecular abundances, or the very structural integrity of objects traversing our solar system. It is conceivable that 3I/2023A3 Suchinchen Atlas represents not a message from intelligent beings, but a communication from the cosmos itself, informing us that the constituents of life are universally present and constantly being redistributed, woven into the very fabric of the galaxy. This concept ventures into territory that often makes scientists uncomfortable. The notion that the universe possesses something akin to intentionality, that chemistry and biology are not random occurrences, but are directed by some underlying organizing principle, is typically rejected outright by most researchers. The prevailing view is that physics is physics, and chemistry is chemistry. Emergent complexity does not necessitate a designer. However, it is valuable to confront this discomfort because the alternative, the profound solitude of existing in a vast, cold, and indifferent universe, presents its own form of cosmic dread. Perhaps the truth lies somewhere between these extremes. It is possible that the universe is not actively attempting to communicate, yet it is replete with information nonetheless. These are patterns awaiting decipherment by any entity possessing the intellect to observe them. Part 11. Quasi-Lunar Moon 2025 PN7, Earth's Tilted Companion. While 3I/2023A3 Suchinchen Atlas captured headlines with its interstellar chemical findings, another discovery was subtly reshaping our understanding of near-Earth space. In August of 2025, astronomers confirmed the existence of 2025 PN7, a small asteroid traversing a peculiar, highly inclined orbit that maintains it in a loose gravitational embrace with Earth. This object is classified as a quasi-satellite, a category of celestial bodies that orbit the Sun but, from Earth's perspective, appear to orbit our planet. The gravitational interplay is intricate, involving a three-body system comprising the Sun, Earth, and the asteroid, resulting in a trajectory that loops around Earth without ever being truly captured. Quasi-satellites are uncommon, but not unprecedented. Earth hosts several known quasi-satellites at any given time. These are typically small, rocky bodies, usually a few dozen meters in diameter, that become temporarily ensnared in resonant orbits. They persist in these orbits for decades, or even centuries, before gravitational perturbations from other planets dislodge them, sending them on new trajectories elsewhere in the solar system. What distinguishes 2025 PN7 is its orbital inclination, tilted approximately 40 degrees relative to Earth's orbital plane. Most quasi-satellites possess low inclinations, circling near the ecliptic plane where gravitational interactions with Earth are most potent. PN7's pronounced tilt suggests an arrival from an unusual angle, potentially originating from the main asteroid belt following a close encounter with Mars or Jupiter that altered its orbital path. This discovery underscores the remarkable dynamism of near-Earth space. We tend to perceive the Moon as Earth's sole celestial companion, but the reality is far more complex. A significant population of small bodies exists in gravitational association with our planet. Some, like PN7, are temporarily captured, while others co-orbit at stable Lagrange points, where gravitational forces achieve equilibrium. The Trojan asteroids located at Earth's L4 and L5 points, discovered only within the past 2 decades, serve as another illustration of this phenomenon. These populations are in a constant state of flux, with objects entering and exiting these arrangements on timescales ranging from years to millennia. What appears as empty space is, in fact, a bustling neighborhood populated by rocks, each following its own intricate path through the gravitational landscape. Connecting this back to 3I/2023 A3 Atlas, it highlights that unexpected celestial behavior is more prevalent than we typically assume. We are accustomed to the predictable orbits of planets, following Keplerian paths that can be calculated centuries in advance. However, the introduction of small bodies, gravitational perturbations, and non-gravitational forces transforms the system into a chaotic environment. Comets exhibit unpredictable variations in brightness. Asteroids tumble erratically. Quasi-satellites execute complex loops around Earth, their trajectories so intricate that they necessitate numerical integration for accurate modeling. And on rare occasions, an interstellar visitor arrives at high velocity, following a trajectory originating entirely outside the solar system. The universe is inherently untidy, and the more meticulously we observe, the more surprises we uncover. The detection of 2025 PN7 showcases advancements in survey technology. The Asteroid Terrestrial Impact Last Alert System, ATLAS, employing multiple wide-field telescopes, scans the night sky nightly to identify moving objects that could pose an impact risk. While its primary function is to detect asteroids on Earth-crossing orbits, it inevitably discovers other celestial phenomena. These include distant comets, quasi-satellites, and interstellar objects like 3I/2023 A3 Atlas. As survey technology continues to improve, with telescopes growing larger and detectors becoming more sensitive, the rate of discovery accelerates. We are identifying hundreds of new asteroids each month, and each discovery contributes to our understanding of the solar system's small body populations. Here is an intriguing detail. Quasi-satellites can remain gravitationally bound to Earth for decades, sometimes centuries, following orbits so convoluted they appear as tangled knots when plotted in three-dimensional space. PN7 is expected to remain in its current configuration for approximately 50 to 100 years before gravitational perturbations dislodge it from its resonant orbit, causing it to drift away. During this period, it will loop around Earth multiple times annually, consistently maintaining a distance of roughly 20 million kilometers. It will never come sufficiently close to be captured into a true orbit, nor will it wander far enough to completely break free. This represents a cosmic ballet choreographed by gravity, unfolding unnoticed unless astronomers happen to direct a telescope toward the correct region of the sky at the opportune moment. And now, for some imaginative speculation, what if something were to conceal itself amongst these objects observing us? Quasi-satellites offer an ideal vantage point for extended observation of Earth. They possess sufficient orbital stability to loiter for decades, yet are distant enough to avoid immediate detection. A hypothetical probe, disguised as a small asteroid, could occupy a quasi-satellite orbit, passively observing our planet, recording electromagnetic emissions, and mapping atmospheric composition, all while appearing entirely natural. We would likely not detect its presence unless we conducted extremely close examination, and even then, it would probably be classified as just another unremarkable rock. While this notion might evoke a sense of paranoia, it is not entirely beyond the realm of plausibility. If one desired to examine a populated celestial body without revealing their presence, establishing a sentinel in a quasi-satellite trajectory would be an astute maneuver. Forthcoming examinations will corroborate PN7's genesis, discerning whether it originated as a celestial fragment from the principal asteroid belt or, more tantalizingly, a shard from a celestial nomad originating beyond our solar system. Spectroscopic analysis holds the key to its elemental makeup, illuminating whether it comprises common silicate rock or something more extraordinary. Photometric measurements will chart its rotational period and seek indications of internal architecture. Should any deviation, be it chemical or physical, be discovered, it would deepen the enigma. Nevertheless, it is most probable that it is merely a terrestrial fragment, an unremarkable piece of stone that chanced to enter a harmonic orbit with Earth for a duration before continuing its journey. Despite this, the very capacity to detect these entities, ascertain their characteristics, and track their celestial paths underscores the remarkable advancements in our observational prowess. This resonates with a larger overarching concept. The cosmos is replete with wonders awaiting discovery at the very threshold of our perceptive capabilities. Every enhancement in telescope sensitivity, every new survey meticulously scanning the heavens, unveils phenomena previously unknown. Quasi-satellites, comets from distant stars, Trojan asteroids converging at Earth's Lagrangian points, objects traversing in retrograde paths. Our solar system presents a complexity and dynamism far exceeding the depictions found in mid-20th century educational materials. And if our immediate celestial vicinity is so abundant with unexpected findings, one can only contemplate the marvels awaiting in the broader galaxy, perhaps too faint or too remote for present instrumentation, yet within the grasp of future generations. Part 12, Next Generation Observational Apparatus, Europe's foremost endeavor commences operations. October of the year 2025 marked another significant achievement. The European Southern Observatory's foremost telescope concluded its initial setup and commenced scientific investigations. Foremost is an acronym signifying a 4-meter multi-object spectroscopic telescope. This nomenclature aptly encapsulates the instrument's core function. It transcends being merely a telescope. It is a spectroscopic survey engine, capable of simultaneously observing 2,400 celestial targets, acquiring spectral data from each, and processing millions of observations throughout its projected operational lifespan. Should the objective be to compile a comprehensive chemical cartography of the Milky Way, or to categorize every comet and asteroid within the inner solar system, or to comprehend the processes of galactic evolution by assessing the composition of countless stars, Foremost is the indispensable instrument. The underlying technology, though seemingly straightforward, is remarkably potent. A primary mirror spanning 4 meters gathers incoming light, and an assembly of automated fiber optic positioners directs this light from individual targets into spectrographs. Each fiber, approximately the width of a human hair, can be precisely positioned anywhere within the telescope's field of view, effectively creating a switchboard that channels light from thousands of objects into instruments that meticulously dissect it into spectral components. These spectra then reveal the chemical makeup, temperature, velocity, and indeed all the physical information encoded within starlight or the reflected solar illumination from a comet. Furthermore, the automated nature of the system, enabling seamless transitions between targets without manual intervention, allows it to survey vast expanses of the sky within a single night. The data procured by Foremost will be instrumental in classifying minor bodies within the solar system, differentiating between various asteroid classifications, identifying comets disguised as asteroids, and intercepting interstellar visitors prior to their perihelion passage. The compositional data acquired by Foremost will be integrated into models of planetary formation, thereby refining our comprehension of how volatile substances like water and carbon are distributed during the tumultuous initial stages of planetary system assembly. If the object designated 3 Atlas were to traverse a trajectory that intersected with Foremost's observational footprint, the telescope would automatically capture its spectrum, flagging it as an object of interstellar origin based on its velocity and composition within a mere few hours of its detection. This brings us to the matter of interstellar object detection. The manner in which next-generation instruments could identify objects akin to 3 Atlas at an earlier stage, thereby affording more time for subsequent observational campaigns. Mixord detected hydroxyl from Atlas only during a specific temporal window, when geometric conditions and chemical properties were optimally aligned. However, had knowledge of Atlas's existence been acquired months earlier, and had optical surveys detected it while it was still situated in the outer reaches of the solar system, radio astronomers would have had the opportunity to pre-plan their observations, meticulously track the initiation of volatile release, and quantify the escalation of hydroxyl production as the comet drew nearer to the Sun. Early detection fundamentally transforms the scientific study of interstellar objects from a series of opportunistic observations into systematic, well-orchestrated campaigns, and instruments such as Foremost are pivotal in facilitating this advancement. European and South African observational facilities are now harmonized for prompt responsiveness. When Foremost or any other optical telescope identifies an anomalous object, this detection triggers automated alerts dispatched to radio observatories like MikeSort, infrared telescopes such as the Very Large Telescope, and orbital platforms like the James Webb Space Telescope. Within hours, a multitude of instruments can commence observations, collaboratively constructing a multi-wavelength depiction of the object before it diminishes in brightness or exits the observable range. This level of inter-instrument coordination, unattainable merely 20 years ago, has now become routine, facilitated by shared data repositories, standardized alert protocols, and international collaborations that transcend geographical and organizational boundaries. Foremost's contribution to the creation of chemical atlases of the Milky Way extends beyond the confines of our solar system. The telescope is slated to analyze spectra from millions of stars, meticulously charting the variations in chemical composition as a function of stellar age, galactic location, and kinematic characteristics. Over time, these measurements will elucidate the galaxy's evolutionary history, illustrating how gaseous matter coalesced into stars, how supernova events enriched the interstellar medium with heavier elements, and how stellar migration redistributed these elements across vast interstellar distances spanning thousands of light-years. This constitutes a form of galactic archaeology, utilizing chemical signatures to reconstruct events that transpired billions of years ago. And here lies a speculative contemplation. What if the next enigmatic signal emanates not from an interstellar visitor like 3 Atlas, but from the very heart of our galaxy? The galactic center is a crucible of activity, a region dominated by a supermassive black hole orbitoed by dense stellar clusters, molecular clouds, and magnetic fields of such immense strength that they can accelerate particles to speeds approaching that of light. Radio observations have unveiled peculiar filamentary structures, enigmatic energetic bubbles, and ephemeral events that defy straightforward interpretation. Foremost possesses the potential to capture the optical counterparts to these radio signals, thereby correlating spectral features with specific physical processes and identifying molecules within environments that are currently beyond our direct comprehension. It is conceivable that the universe is engaged in continuous broadcasting, not from extraterrestrial civilizations, but from the galaxy itself, and we are now developing instruments with sufficient sensitivity to decipher this cosmic message. Let us draw a parallel between Foremost and MikeSort's distinct but complementary roles. Foremost operates in the optical spectrum, while MikeSort is a radio telescope. Radio telescopes are adept at detecting molecules, providing insights into the chemistry of interstellar gas and dust. Optical telescopes, conversely, excel at observing atoms, revealing the physics governing stars and the reflection of sunlight. Infrared telescopes are sensitive to thermal radiation, capturing the glow emitted by planets and dust clouds. Ultraviolet telescopes are attuned to high-energy phenomena, such as shock waves and intense radiation originating from hot stars. Each spectral range unveils a distinct facet of reality, and only by synthesizing the data from all of them can a comprehensive understanding be achieved. The spectral lines of hydroxyl detected from 3 Atlas offer crucial information about water chemistry. The optical spectra provide details on dust composition and surface reflectivity. Infrared data illuminate temperature and the rates of volatile sublimation. When all this information is integrated, it provides a holistic understanding of the object's nature, origin, and evolutionary trajectory. Synergy in large-scale surveys represents the vanguard of cosmic discovery. No single instrument, irrespective of its power, can provide definitive answers to every scientific inquiry. A network of interconnected instruments, operating across the entire electromagnetic spectrum and coordinated by automated alert systems, is essential. These systems must feed data into shared repositories, accessible to researchers worldwide. This paradigm shift is currently underway, marking a transition from singular, heroic observational efforts to collaborative endeavors that harness the collective capabilities of numerous facilities simultaneously. Consequently, the pace of discovery is accelerating. An increasing number of interstellar objects, exoplanets, transit phenomena, and detailed chemical maps of star-forming regions are becoming available in astronomical databases at a rate that surpasses the capacity of any individual scientist to fully process. Part 13, Dark Matter, Subtle Indications within Pulsar Signal Patterns. Now, we shift our focus from interstellar travelers to a more profound enigma: anomalies within the very fabric of spacetime. Throughout the year 2025, pulsar timing arrays, which consist of interconnected radio telescopes monitoring dozens of rapidly spinning pulsars distributed across the galaxy, have been reporting peculiar observations. The signals emanating from these pulsars, functioning as cosmic chronometers that rotate hundreds of times per second and emit radio pulses towards Earth with exceptional regularity, are exhibiting minute deviations from their expected timing. These discrepancies are exceptionally small, measured in nanoseconds over periods of months, yet they possess statistical significance. More critically, these deviations are correlated. When the timing of one pulsar shifts, other pulsars exhibit similar shifts in a manner that suggests an underlying phenomenon is alternately stretching and compressing the intervening space between us and them. Pulsars are the remnant cores of massive stars that have undergone supernova explosions. These are neutron stars, so incredibly dense that a mere teaspoonful of their material would possess a mass exceeding that of Mount Everest. They rotate at astonishing speeds, often hundreds of revolutions per second, and their magnetic fields are so formidable that they channel radiation into narrow beams, sweeping across the cosmos like the beams of lighthouses. If Earth happens to lie within the path of one of these beams, we perceive a pulse each time the neutron star completes a rotation. Given the remarkable stability of this rotation, pulsars serve as exceptionally precise natural clocks, some even surpassing the accuracy of atomic clocks on Earth. Pulsar timing arrays leverage this inherent precision to search for gravitational waves, which are ripples in spacetime predicted by Einstein's theory of general relativity. When a gravitational wave propagates through the galaxy, it causes localized distortions in spacetime, stretching space in one direction while compressing it in another. This, in turn, induces minute alterations in the distances between Earth and distant pulsars, manifesting as timing variations. Pulse signals arrive slightly earlier or later than anticipated, depending on whether the gravitational wave has elongated or shortened the spatial path traversed by the light. By simultaneously monitoring numerous pulsars, astronomers can discern the characteristic signature pattern indicative of gravitational waves. These correlations serve to distinguish genuine spacetime distortions from random noise. And it is precisely such correlated signals that pulsar timing arrays have been detecting: ultra-low-frequency gravitational waves with oscillation periods ranging from years to decades, significantly longer than the millisecond period waves previously detected by instruments like LIGO and Virgo. The prevailing hypothesis suggests these waves originate from supermassive black hole binaries, pairs of black holes, each possessing a mass millions or billions of times that of the Sun, spiraling towards a merger within the cores of distant galaxies. As these behemoths orbit each other, they agitate the space-time continuum, much like a spoon stirring honey, generating gravitational waves that propagate outwards at the speed of light. By the time these waves reach Earth, they have become exceedingly faint, causing minimal perturbation to the fabric of space-time, yet they are within the detection capabilities of pulsar timing arrays. However, this is where speculation enters the discourse. Certain theoretical frameworks propose that the observed signal might not be attributed to gravitational waves generated by black holes. Instead, it could be a manifestation of dark matter. This hypothesis deviates from the conventional models that favor cold, weakly interacting particles. Instead, it posits the existence of more exotic entities, such as oscillating fields or topological defects within spacetime, relics from the nascent universe. Dark matter constitutes the dominant mass component of the galaxy, outweighing ordinary baryonic matter by a ratio of 5:1. Despite its pervasive influence, direct detection of dark matter has remained elusive. Every experimental endeavor designed to capture dark matter particles has, thus far, yielded null results. Perhaps dark matter is not composed of discrete particles at all. It might exist as waves, as fluctuations within an as yet unidentified field. These fluctuations, in turn, could interact with spacetime in ways that mimic the signatures of gravitational waves. This concept bears a metaphorical resemblance to the notion that the cosmos itself possesses a pulse, that an underlying rhythm governs the very nature of reality. Pulsars rotate, black holes orbit, gravitational waves oscillate, and even the expansion of the universe experiences periods of acceleration and deceleration, dictated by the intricate balance between matter and dark energy. Every element within the cosmos appears to adhere to cyclical patterns, repeating phenomena that emerge from fundamental physical principles. It is plausible that these patterns represent a form of communication, not intentionally directed, but inherently informative, broadcasting the fundamental structure of reality to any entity capable of its measurement. Let us highlight the parallels. Both pulsar timing analysis and the study of hydroxyl absorption phenomena rely on highly precise frequency analysis. In pulsar timing, the frequency of radio pulses is meticulously measured, tracking minute variations over extended observation periods. In spectroscopy, the frequencies of light absorbed or emitted by molecules are precisely determined, enabling the identification of chemical species through spectral line widths measured in the sub-megahertz range. Both methodologies push the boundaries of measurement precision to extraordinary levels, extracting valuable information from signals that are so faint they are barely discernible above background noise. Furthermore, both techniques unveil phenomena that would otherwise remain invisible without such exacting measurements, gravitational waves in one instance and molecular abundances in the other. Now, let us engage in speculation. Could interstellar objects be influenced by galactic-scale rhythmic phenomena? If gravitational waves emanating from binary supermassive black holes continuously permeate the galaxy, could they exert subtle influences on matter, perhaps altering orbital dynamics or triggering outgassing events on comets? The forces involved are unimaginably minuscule, far too weak to measurably affect a macroscopic object. However, over millions of years, and across billions of celestial bodies, could cumulative effects lead to observable consequences? This line of inquiry is highly speculative, bordering on fringe science, yet it is precisely the type of questioning that occasionally leads to profound scientific breakthroughs. The universe, after all, is interconnected in ways that we are only beginning to comprehend. The distinction between seemingly unrelated phenomena and subtle causal relationships is often far more tenuous than we initially assume. It is crucial to emphasize the inherent mystery. As of yet, there is no definitive explanation for the observed anomalies in pulsar timing data. Nevertheless, these findings are already reshaping the landscape of astrophysics. If the detected signal indeed represents gravitational waves from binary black holes, it would serve as confirmation of predictions regarding supermassive black hole mergers and validate general relativity within a novel observational domain. If, conversely, the signal originates from an alternative source, such as dark matter or some hitherto unknown physical principle, then humanity stands on the precipice of a paradigm shift that could fundamentally alter our understanding of the cosmos. Regardless of the ultimate explanation, the data itself is irrefutable, the correlations are statistically significant, and the phenomenon responsible is operating on scales that dwarf anything within our everyday experiential realm. This realization propels us toward the next frontier of cosmic exploration, not through radio waves or gravitational phenomena, but through the study of light itself. While radio telescopes are adept at listening to the molecular intricacies of space, and pulsar timing arrays are measuring distortions in spacetime, optical and infrared instruments are diligently mapping entire planets with unprecedented detail. They are revealing the atmospheric chemistry of exoplanets, even those light years away, utilizing methodologies analogous to those employed in the study of 3 Atlas. Part 14. JWST's three-dimensional map of an ultra-hot Jupiter's atmosphere. In November of the year 2025, the James Webb Space Telescope delivered one of its most remarkable scientific results to date, a comprehensive three-dimensional temperature map of the atmosphere of the exoplanet WASP-18b. This celestial body is a gas giant, possessing a mass approximately 10 times that of Jupiter, and orbits its host star so closely that its orbital period, its year, is less than a single Earth day. The planet is tidally locked, meaning one hemisphere perpetually faces its star, while the opposite hemisphere remains in eternal darkness. Through the application of infrared spectroscopy, precisely tracking the variations in the planet's thermal emission as it orbits its star, JWST has now successfully mapped the temperature distribution across its entire surface. This has revealed intricate wind patterns, localized hot spots, and chemical gradients that collectively narrate the story of an atmosphere in a state of extreme and violent turbulence. WASP-18b is classified by astronomers as an ultra-hot Jupiter, a category of exoplanets orbiting their host stars at such extreme proximities that their dayside temperatures surpass 2,500 Kelvin, a thermal state sufficient to vaporize most metallic elements. Its atmosphere is a volatile crucible of exotic chemistry, containing gaseous iron, titanium oxide, and water vapor that has undergone thermal dissociation into its constituent elements, hydrogen and oxygen. The dayside radiates intensely in the infrared spectrum, emitting heat as if from a colossal blast furnace. The night side, deprived of direct stellar illumination, would be expected to be considerably cooler, perhaps reaching temperatures of 1,000 Kelvin or less. However, JWST's observations revealed an unexpected finding. The night side is demonstrably hotter than current theoretical models had predicted. This suggests that powerful atmospheric currents are transporting heat from the day side at a rate significantly exceeding prior estimations. The process of three-dimensional mapping is achieved by analyzing phase curves, which involves meticulously tracking the fluctuations in the planet's infrared brightness as it traverses its orbital path around its star. When the planet's day side is oriented towards Earth, the planet appears brightest in infrared observations. Conversely, when the night side is facing us, its infrared brightness diminishes. By quantifying this brightness at multiple distinct wavelengths throughout the orbital cycle, JWST is capable of reconstructing the temperature distribution at various altitudes and longitudinal positions. The incorporation of spectroscopy further refines this analysis. By identifying specific molecules that absorb or emit radiation at particular wavelengths, a chemical map can be overlaid onto the temperature map. This allows for the pinpointing of carbon monoxide concentrations in one region, the presence of water vapor in another, and the formation of titanium oxide clouds at specific atmospheric layers. This technique bears a direct connection to the study of 3 Atlas. Both methods rely on the principle of molecular absorption to infer composition. The spectral lines of hydroxyl observed from Atlas provide evidence of water dissociation within the comet's coma. Similarly, the spectral features detected within the atmosphere of WASP-18b indicate the presence of specific molecules at particular temperatures and pressures. The underlying physics governing these observations is identical, merely applied across different scales. In both scenarios, the fundamental principle exploited is the characteristic absorption and emission of light by molecules at specific frequencies, a phenomenon dictated by quantum mechanics. These frequencies act as unique spectral fingerprints for each molecular species, enabling their identification without the need for direct physical sampling. This highlights the technological overlap. The analytical principles are consistent across vastly different scales. Whether observing a comet located 100 million kilometers away or an exoplanet situated hundreds of light years distant, the fundamental technique remains the same: collect incoming light, disperse it into a spectrum, and identify absorption or emission features. These features are then matched to known molecular transitions, allowing for the inference of the physical conditions necessary for their production, such as temperature, pressure, density, and chemical abundance, all encoded within the characteristic shape and intensity of spectral lines. This represents one of the most potent tools in the astronomical arsenal, and advancements in detector sensitivity and spectral resolution have transformed it from a rudimentary diagnostic instrument into a highly precise probe of remote celestial environments. JWST is capable of detecting phase curves as planets orbit their host stars, generating detailed maps of heat distribution with exceptional accuracy. The telescope's infrared instruments, maintained at cryogenic temperatures to minimize their own thermal emissions, can discern temperature variations of mere Kelvin across an exoplanet's atmosphere. This is a remarkable feat, considering that the planet appears as an unresolved point of light, millions of times fainter than its parent star. The methodological approach involves conducting numerous observations as the planet completes its orbit, thereby subtracting the star's constant brightness to isolate the planet's variable contribution. Across dozens of observations spanning a full orbital period, the planet's thermal signature emerges from the background noise, revealing not only its average temperature, but also the intricate distribution of heat across its global surface. This provides a powerful illustration of the progressively increasing precision of humanity's observational capabilities. 50 years ago, the mere detection of an exoplanet seemed an insurmountable challenge. 20 years ago, astronomers could ascertain their masses and orbital periods, but information regarding their atmospheres remained largely inaccessible. A decade ago, transmission spectroscopy enabled the detection of water vapor and other molecules as planets transited their stars. Now, with the advent of JWST, we are capable of mapping three-dimensional atmospheric structures, tracking meteorological patterns, and identifying chemical gradients. This progression is demonstrably exponential. Each successive generation of instruments reveals layers of detail that were imperceptible to its predecessors. Should our current trajectory persist, and as we construct progressively larger observing instruments in the ensuing decades, humanity will ultimately achieve the capacity for direct exoplanet imaging. This advancement will allow us to discern their surface features, actively seek out biosignatures, and potentially even detect manufactured illumination or atmospheric contamination originating from technologically advanced civilizations. Let us ponder this. If we can meticulously chart the atmospheric compositions of exoplanets, might we one day similarly map interstellar visitors with comparable detail? The object designated 3I Atlas, being too diminutive and faint, falls outside the scope of direct imaging. However, future instruments endowed with superior spatial resolution and heightened sensitivity could potentially resolve its nucleus, allowing us to map surface temperature variations and identify localized energetic emissions and active zones. Undertaking spacecraft missions to interstellar bodies, while presenting considerable technological hurdles owing to their immense velocities and the limited advance warning they afford, possesses the potential to fundamentally reshape our comprehension of such phenomena. Envision a probe equipped with sophisticated spectrometers, cameras, and mass spectrometers traversing the gaseous envelope of an interstellar comet, directly analyzing its constituent materials. The scientific dividends from such an endeavor would be truly extraordinary, providing pristine matter from an alien star system, untouched by the processes of our own solar system, and examined in situ with instruments far surpassing the capabilities of any terrestrial observatory. We have already witnessed discoveries of remarkably exotic molecular compounds within the atmosphere of WASP-18b. The James Webb Space Telescope has not only detected carbon monoxide, water vapor, and titanium oxide, but has also provided hints of more intricate species, possibly silicon monoxide, or even molecular fragments entirely absent from Earth's atmospheric constituents. The chemical dynamics of ultra-hot Jupiters are intrinsically alien, governed by temperatures and pressures that are not naturally encountered within our solar system. Comprehending this unique chemistry broadens our perspective on the potential for molecular formation under extreme conditions and illuminates how atmospheric circulation facilitates their transport and redistribution. Each exoplanet observation serves as an unparalleled experimental test, one that would be impossible to replicate on Earth, showcasing nature's capacity to push matter to its absolute limits. This meticulous mapping endeavor transcends the traditional boundaries between astronomy and planetary science. Astronomy has historically treated celestial objects as mere points of light, measuring their luminosity and spectral signatures without the ability to resolve their surfaces or internal architecture. Planetary science, conversely, involves close-up examination of objects, utilizing spacecraft to map terrain, analyze samples, and unravel geological processes. However, with the relentless improvement of our instruments, this distinction is rapidly dissolving. The James Webb Space Telescope is now capable of studying exoplanet atmospheres with a level of detail comparable to the earliest spacecraft investigations of our own solar system's planets. Future observatories, particularly space-based interferometers designed for direct imaging, will further blur this line. We will eventually study planets orbiting distant stars with the same rigor we apply to Mars or Venus, meticulously charting their surfaces, tracking seasonal shifts, and actively searching for evidence of geological or biological activity. The relentless influx of data is fundamentally altering our cosmic perspective. Between the identification of interstellar objects, the detailed atmospheric profiles of exoplanets, anomalies in pulsar timing, and the impending deployment of next-generation survey instruments, we are living through an epoch of discovery unmatched in human history. This accelerating pace is fueled by technological innovation, but also by the dawning realization that the universe is far more bewildering and intricate than mid-20th century scientific understanding had anticipated. Each new observation precipitates further questions, and every answer unearthed reveals even deeper mysteries. The instruments currently under development, from the Vera C. Rubin Observatory to forthcoming radio telescope arrays, will undoubtedly push these frontiers even further, transforming astronomy from a purely descriptive discipline into one of active exploration, where the ultimate objective is not merely to catalog the cosmos, but to comprehend its intricate interconnectedness. Part 15. The Rubicon Shift. Billions of new solar system objects revealed by the Vera C. Rubin Observatory. We stand at the precipice of a culmination, a pivotal juncture where all these disparate threads converge into a single, transformative moment for astronomy. In late 2025, the Vera C. Rubin Observatory in Chile is set to conclude its final commissioning tests, after which it will commence full scientific operations. When this occurs, and the legacy survey of space and time officially begins, astronomy will irrevocably cross a threshold. Within its inaugural year of operation, the Vera C. Rubin Observatory will identify more solar system objects than humanity has catalogued throughout all preceding centuries combined. It will detect interstellar visitors months in advance of their closest approach, enabling coordinated observations that would have been utterly impossible with instruments like the three-body atlas. This observatory will revolutionize our understanding of the solar system, transitioning it from a static inventory of known bodies to a dynamic cinematic record of celestial motion. The sheer scale of its capabilities is astounding. The Rubin Observatory's 8.4-meter primary mirror and its wide-field camera, the largest digital camera ever constructed, will survey the entirety of the visible sky every few nights, generating a 10-year time-lapse chronicle of the universe. Every asteroid, every comet, and indeed every object that exhibits motion against the backdrop of stars will be automatically detected, tracked, and catalogued. Current projections indicate that the Rubin Observatory will discover approximately 5 million new asteroids in the main belt, hundreds of thousands of Kuiper belt objects beyond Neptune, and a conservative estimate of dozens of interstellar visitors throughout its operational lifespan. This latter figure is notably conservative. In a mere 8 years, we have detected 3 interstellar objects using surveys that cover only a small fraction of the sky. The Rubin Observatory, however, will conduct a comprehensive survey, capturing objects that previous instruments missed due to their faintness, excessive speed, or unfortunate positioning in the sky. The 10-year Legacy Survey of Space and Time, or LSST, is far more than a mere asteroid survey. The same observational data that tracks moving objects also reveals supernovae, quasars, gravitational lensing events, and virtually anything that undergoes changes in brightness or position on timescales ranging from seconds to years. Astronomers will leverage LSST data to investigate dark energy, the enigmatic force responsible for the accelerating expansion of the universe. They will map the intricate structure of the Milky Way, charting stellar movements and identifying stellar streams gravitationally dislodged from disrupted galaxies. Furthermore, they will search for optical counterparts to gravitational wave events detected by LIGO and Virgo. The sheer breadth of scientific inquiry facilitated by a single telescope is almost beyond comprehension. This is achievable because the Rubin Observatory does not merely capture aesthetically pleasing images. It generates a vast database, a digital representation of the sky that can be mined for discoveries long after the initial observations have been made. The Rubin Observatory is poised to revolutionize the detection of interstellar objects, identifying them months in advance. The Object 3 I Atlas was discovered in July 2025, a mere few months prior to its closest approach to the Sun in October. This limited timeframe afforded researchers insufficient opportunity for coordinated observations, telescope time requests, and campaign planning. Had the Rubin Observatory been operational, it would have detected Atlas considerably earlier, potentially while it was still traversing the outer reaches of the solar system, faint but discernible against the stellar background. Early detection translates into immediate alerts, automated notifications dispatched to observatories worldwide, granting radio telescopes, infrared instruments, and spacecraft mission planners several months to prepare. Imagine meticulously tracking an interstellar comet from the moment it crosses Neptune's orbital path inward, observing its increasing brightness, identifying the onset of volatile activity, and precisely measuring the evolution of its tail and coma as it approaches the Sun. This is the future that the Rubin Observatory is enabling. The observatory will process tens of terabytes of data each night, a volume far exceeding any human capacity for review. Consequently, the discovery process is entirely automated, employing machine learning algorithms trained to recognize moving objects, distinguish them from instrumental artifacts, and classify them based on their orbital characteristics and photometric properties. Should an object exhibit unexpected velocity, possess a hyperbolic orbit, or display spectral characteristics inconsistent with known asteroid classes, the system flags it for further investigation. Within hours of detection, anomalous objects can be brought to the attention of astronomers, who can then initiate requests for supplementary observations or alert other astronomical facilities. This rapid response capability, unprecedented before the advent of machine learning and distributed databases, is precisely what will enable the capture of the next 3I Atlas before it becomes another lost opportunity. If an object like 3I Atlas were to appear today, the Rubin Observatory would have detected it long before any significant signal was perceived. The detection of hydroxyl on October 24th would not have been a surprise discovery, but rather the culmination of a month-long observing campaign. Radio telescopes could have maintained continuous monitoring of the comet, tracking the escalation of volatile production as it neared the Sun. Spacecraft, contingent on funding and trajectory optimization, could have been rerouted for a flyby. International collaborations would have synchronized multi-wavelength observations from both ground-based and spaceborne instruments, thereby constructing a comprehensive understanding of the object's composition, structure, and behavior. Instead, we were afforded a single radio detection within a narrow temporal window, tantalizing yet incomplete. This distinction marks the difference between serendipitous snapshots and systematic investigation. A century ago, the discovery of a new asteroid was a significant event, warranting publication and celebration. Today, automated surveys identify hundreds each night, and only those exhibiting unusual characteristics, such as Earth-crossing orbits or peculiar spectral properties, merit detailed attention. Within a decade, interstellar objects will transition from being rare, decade-defining sensations to routine occurrences, systematically identified, cataloged, and studied as integral components of ongoing surveys. This normalization is simultaneously exhilarating and sobering. It is exhilarating because it signifies that we will accumulate data at a rate sufficient to address statistical questions. How prevalent are interstellar visitors? What is the distribution of their sizes and compositions? Do they concentrate near the ecliptic plane or arrive from arbitrary directions? It is sobering because each individual discovery will relinquish its singular status, becoming merely a data point within a larger dataset rather than a standalone event. Let us speculate. What if 3I Atlas was not an anomaly, but simply the first emissary to announce itself? Perhaps interstellar objects have been continuously traversing our solar system, numbering in the tens or hundreds annually, but have remained undetected due to their faintness and high velocities. The Rubin Observatory will reveal them. And when it does, when we begin to observe dozens each year instead of one every few years, we will come to realize that the galaxy is far more interconnected than we had previously conceived. Matter does not remain confined to its originating system. It is continuously redistributed, intermingled, and shared across stellar neighborhoods. Every planetary system constantly receives and contributes mass, with comets ejected through gravitational interactions becoming infall objects for other systems. The galaxy functions as a network, not a collection of isolated islands, and the traffic between these nodes is far more substantial than we had ever imagined. The hydroxyl signature detected from 3I Atlas provided insights into the chemistry of another star system. The geometric configuration of its trajectory and the timing of its detection underscored the rarity and preciousness of such observations. The enigma surrounding its anomalies, including deviations in its trajectory and the formation of its tail, serves as a potent reminder that even natural celestial bodies can exhibit behaviors that challenge our established models. Furthermore, the coincidence of its proximity to the region associated with the "wow" signal, whether coincidental or not, ignites our collective imagination, for we are a species predisposed to seeking patterns and yearning for the universe to impart some form of communication. The universe, in its capacity as a communicator, may not do so in an anthropocentric sense, with messages deliberately directed at us, but rather in a more profound sense, wherein all phenomena intrinsically carry information. Every photon encodes the conditions of its emission. Every molecular spectral line reveals temperature and density. Every orbital path traces a history of gravitational interactions. The cosmos is not silent. It is continuously broadcasting across every wavelength and at every conceivable scale. Our challenge lies not in detecting the signal itself, but in deciphering its language, in constructing the instruments, and in developing the conceptual frameworks that enable us to translate physical phenomena into genuine understanding. Perhaps the cosmos has been subtly communicating all along, and it is only now that we are truly attuned to its whispers. 3I Atlas, with its distinctive hydroxyl signature and enigmatic behavior, was not the inaugural interstellar visitor to transport water and organic compounds through our solar system. It was merely the first one we were able to perceive. How many others have passed undetected? How many will we identify in the coming years as our observational capabilities improve and our survey areas expand? And what profound revelations will these wanderers, these icy emissaries from distant suns, offer regarding the prevalence of complex chemistry and the potential for life across the vast expanse of the galaxy? The narrative of 3I Atlas extends beyond the story of a single comet on a unique trajectory. It represents the journey of a species learning to interpret the universe, developing the technological prowess and conceptual tools necessary to decipher signals that would have been unimaginable a century ago. Radio telescopes are now discerning molecular compositions. Optical surveys are meticulously tracking celestial motion across the sky. Infrared instruments are mapping temperatures on worlds light years away, and pulsar timing arrays are measuring the subtle ripples within spacetime itself. All these efforts are converging, collectively revealing a cosmos far richer and more astonishing than we had ever dared to hope. And perhaps, just perhaps, one day we will detect something that defies explanation through natural processes alone. A signal possessing a complexity too structured for mere chemistry, a trajectory too precise for the vagaries of gravity, a pattern too ordered for the inherent chaos of the universe. Should that momentous day arrive, if it arrives at all, we will be prepared. We will have the instruments, the techniques, and the understanding to distinguish genuine signals from noise, causation from coincidence, and mystery from profound comprehension. Until then, we continue to listen, to observe, and to meticulously catalog every faint whisper from the cosmic darkness, every anomaly within the data, every object that deviates subtly from our established models. For nestled within that overwhelming flood of information, within the terabytes of spectral analyses, images, and timing residuals, may lie the answer to the most ancient question our species has ever posed. Are we alone? While 3I Atlas did not definitively answer this question, it illuminated the path forward, not through deliberate transmissions or obvious beacons, but through the intricate chemistry of molecules traversing interstellar space, through the ice and organic compounds that hold the potential to seed worlds with the very ingredients for life. The subsequent interstellar visitor will undoubtedly offer further insights, as will the ones that follow, and the hundreds or thousands that the Vera C. Rubin Observatory is projected to discover over the next decade. Each represents a valuable data point, refining our understanding and bringing us closer to ascertaining whether the chemistry we detected is a common cosmic phenomenon or a rare occurrence, whether the building blocks of life are ubiquitously present or exceptionally scarce, and whether the universe teems with voices that we are only just beginning to perceive. The signal emanating from 3I Atlas eventually faded as the comet traversed behind the Sun, vanishing once more into the interstellar void. It is now embarking on its outward journey at a velocity of 42 kilometers per second, carrying whatever residual chemistry it still retains towards another star system, a voyage that will span 1,000,000 years. We were granted a singular opportunity to listen, a brief window where celestial mechanics and technological capability aligned. We detected hydroxyl dissociating under stellar radiation, measured its velocity and spectral line widths, and confirmed, for the very first time in human history, that water originating from another star system possesses a sonic signature indistinguishable from that of our own. Now, we await the next such encounter, for they are out there, countless icy bodies drifting through the cosmic darkness. Sooner or later, another will pass close enough for us to hear. When that moment arrives, we will be ready. Our telescopes are vigilant, our algorithms are actively processing data, and our instruments are diligently listening to every subtle whisper from the cosmos, transforming chemical signatures into understanding, celestial motion into historical context, and faint signals into compelling narratives. And perhaps, one of those narratives will ultimately be the one we have yearned for since the moment we first gazed at the stars and pondered the existence of other listeners.